Welcome back, everybody. In this lecture, we're going to be discussing object-oriented programming. Object-oriented programming, or OOP, allows programmers to create their own objects that have methods and attributes, and it's a really great way, once you begin scaling your code, to organize your code. So recall that after we defined things such as a string, list, dictionary, or other built-in Python objects, we were able to call methods off of them with the .method name syntax, such as when we were able to call the append method off of a list object, or the index method off of a tuple. These methods act as functions that use information about the object, as well as the object itself, to return results, or edit or change the current object somehow, such as when you called .sort on a list, it went ahead and edited the current list. For example, this includes appending to a list or counting the occurrences of an element in a tuple. So those methods use information about the object and then either return a result or they edit and change the current object in some manner. OOP, or Object-Oriented Programming, allows users to create their own objects with their own methods and own attributes. And the general format is often confusing when first encountered, particularly because of the use of a self keyword. And its usefulness may not be completely clear at first for beginners. But in general, object-oriented programming allows us to create code that is repeatable and organized, and at a certain scale, you're going to need to understand how to work with object-oriented programming in order to make sure your programs themselves are flexible. And when you're working with outside libraries, you'll see how they make use of object-oriented programming in a lot of their code. So for much larger scripts of Python code, functions by themselves really aren't going to be enough for organization and repeatability. Commonly repeated tasks and objects can be defined with OOP to create code that is more usable, especially across an organization. So let's check out the syntax of object-oriented programming, and don't worry about completely understanding everything we show you right now. We're going to take it step by step in a Jupyter Notebook through a series of lectures. But for right now, I just want to give you a brief overview of some special syntax calls that we haven't really seen before. The first one being the class keyword. So the basic way that you define an object is using the class keyword. And that's why sometimes objects are also called classes in Python. Sometimes people like to interchange those two terms. But basically we have the class keyword and then we have the name of the class. And notice here that the name of the class now is following what's called camel casing, where every individual word has that first letter capitalized, which is why we were telling you before to have variable names and function names in lowercase, because classes, those are the reserved uppercase words and uppercase naming schemes. So we have class, and then we define the name of the class. The next thing we notice here is this thing that looks a lot like a function, but it's actually called a method when it's inside of an object or inside of a class call. And here we have def, just like we would with a function, and we have this special method called init method, and it's underscore underscore init, and this allows you to create an instance of the actual object. You'll notice here we have then a self keyword as well as some parameters to be passed. So param1 and param2 are going to be parameters that Python expects you to pass when you actually create an instance of this object. And then what it does is when you pass in a parameter, for instance parameter 2, you go ahead and assign it to an attribute of the function. That way Python knows that when you're referring to self.param2, you're referring to the attribute param2 that's connected to this actual instance of the class instead of a global variable called param2. And we'll explain this in a lot more detail because this is a step that is really confusing at first. But again, all we're doing here is we're going to pass in a parameter and then connect that parameter with the use of that self.argument or self.parameter to link it to the actual object itself. After that, then we can have various other method calls. And these look a lot like functions. We say def, the name of whatever you want your method to be, and then you pass in that self keyword again to let Python know that this isn't just some function, it's a method that's connected to this class. And that's why we use the self word, to connect these methods to the class so that when you call something like self.param1, it knows that you're referring to the attribute param1 that's connected to the class itself. Okay, so we're going to explore object-oriented programming in a lot more detail, take it really slowly step by step in the next series of lectures. So if that was all kind of a real quick blur for you, don't worry, we're going to go step by step coming up next. We'll see you there. Welcome back, everyone. It's time to actually dive in with Python and use object-oriented programming to create our own objects. In part 1 of this series of lectures, we're going to focus on the class keyword as well as creating attributes for our objects. Let's jump to a Jupyter Notebook and get started. Alright, so let's start off by actually realizing what an object already looks like in Python. If I were to create my list, 1, 2, 3, I would be able to then call the variable myList, say dot, hit tab, and see a bunch of attributes and methods off of this object. And the same thing goes for a set. And we've seen how to create a set using mySet equal to, and then we have this set keyword. And then if I take a look at my set, I can do dot tab and see a bunch of attributes and methods. What we're going to do is see if we can create our own user-defined objects. And everything in Python is an object. So I could say, what is the type of my set? And it will report back that it's a set. And I can do the same thing for that list I just created. It reports back that it's a list. So let's explore how we can use the class keyword to create a user-defined object. So these are built-in objects. Let's use class, that's C-L-A-S-S, that's our keyword here for a user-defined object. The class is basically a blueprint that defines the nature of a future object. And from classes, we can then construct an instance of the object. And an instance is a specific object created from a particular class. So we're going to now create the simplest class possible. So I'm going to say sample. Notice how my class name is capitalized. So by convention, for classes, we follow camel casing, which is to say that every word here starts with a capital letter, unlike snake casing for variable names and function names where we had underscores. So by convention, we use capitalized names for classes. So we have class sample word, and I'm just going to say sample here, open close parentheses, colon, and then we'll say pass. So recall that the pass keyword basically just says don't do anything, and it's a placeholder there. If we didn't have it, we would get some sort of syntax error in the file. So instead we have pass, and that's it. We've just created our first class. And all it's doing is just saying, hey, you create a sample class, and that's it. There's nothing else there. So let's create an instance of the sample class. We'll say my sample is equal to, and then we call sample, open close parentheses. We don't pass in anything into it yet. Shift enter to run that. And if I check the type of my sample, you should see something that lets you know that it's a sample type. All right. So what we've done so far is we used the keyword class, created our own sample class. It doesn't really do anything. Then we created an instance of that class by saying the variable name is equal to an instance of sample. And then we can check my sample, and it says it's main.sample. Later on in the future lecture, we're going to discuss what this underscore underscore main underscore underscore keyword actually means. Basically, it's just letting you know that this particular instance of sample is connected to your main script here. All right, so that's the simplest class possible. It's not very useful though, because it doesn't have any attributes. So let's now see how we can create attributes. So inside of class here, I'm going to write 2 lines of code. I'm going to say def, just like we would for a function, except when it's inside of a class, we refer to this as a method. And this is a special method called the init method, which is going to be called upon whenever you actually create an instance of the class. And we always start off with the self keyword, which basically connects this method to the instance of the class, and it allows us to refer to itself. And then we pass in any attributes that we want the user to define. So for example, instead of calling our class sample, I'm going to say that it's a dog class. So dogs have attributes to them, and an attribute is a characteristic of an object. Later on, we'll discuss methods, which is an operation we can perform with the object, but for right now, we're focusing on attributes. So we may be thinking, well, what kind of attributes or characteristics do dogs have? Well, they have a breed. So something we may want to pass is the breed of the dog. And remember, when we had my set and my list, I could do dot tab and then see a bunch of options. Some of these are methods, some of these are attributes. What we're going to do now is try to create an attribute here so that when I create an instance of the dog class, I can hit dot and then see that breed pop up. So let me delete these lines because we won't need them anymore since the sample class won't be used. And then we will say self dot breed is equal to breed. And these 2 lines can be really confusing at first, since this is the first time we see the self keyword and we see the sort of like strange assignment. but I want to run this first and then break down what's happening in these 2 lines of code. So let's run this, and notice my indentation there. Everything's indented a little bit. And let's create a variable. I will say my dog is equal to an instance of the dog class. Now if I don't pass anything, I will actually get an error. So you'll notice that we actually get an error when we run this with no positional arguments because we are expecting the breed parameter. So what this Python is trying to say to us is, hey, when you create a dog, it's expecting you to pass in a parameter for breed. So let's do that. We're going to say breed of the dog is a lab. And now when we run this, we don't get an error, and I can check the type of this my dog variable, and it says, hey, you now have an instance of the dog class. And if I say my dog dot and then hit tab, I should be able to autocomplete breed. Now the reason breed autocompletes is because right now it's the only attribute. Later on when we add in more attributes, we'll see a drop-down list. But if I run this, it reports back, hey, this instance of the dog class called my dog, its breed is lab. So let's scroll back up here and break down what's going on. Init can basically be thought of as the constructor for a class, and it's going to be called automatically when you create an instance of the class. This self keyword, it represents the instance of the object itself, and actually most object-oriented languages pass this as a hidden parameter to the methods defined on an object. But Python, it doesn't do this. You have to declare it explicitly. And by convention, we use the word self here. Technically, you could write in any variable name you wanted, but you should definitely stick with self. That way other programmers, when they look at your code, it makes sense to them. Now, I want to focus on breed because I found it confusing when I was just beginning that you see breed here 3 times. You see breed, self.breed is equal to breed. And I want to show you something that's not going to be correct convention-wise, but will hopefully help you understand how breed is being worked into this entire object. So what happens is when you create an instance of the dog class, Python is going to call this init method, and it's going to use self in order to represent the instance of the object itself, and then it's going to expect you to pass in this argument, breed. And I'm going to call this my breed. And what happens is when you say my breed here, I can set my breed here, and then you assign the attribute equal to whatever this parameter was. By convention, these 3 have the same name, but I want to show you how changing the name will hopefully make this clear to you what the actual connection is when you pass in the parameter. So I'm going to rerun this. And if I take a look at dog and then do shift tab, and you can also call help on dog, you'll notice that it's expecting my breed to be passed in. So what happens is you pass in this variable for my breed, and then the next step is you take whatever variable was provided for my breed and then set it equal to the attribute .breed or self.breed because this represents the instance of the object itself. So all we're doing when it comes to attributes, which again are characteristics of the object, later on we'll learn about methods, is we take in the argument. In this case, it's my breed, and we assign it using self.attribute name. So that's just the convention of what you're actually typing, self. And then you choose the attribute name. In this case, I'm calling it .breed. So let's run this again. Make sure you rerun this cell so we have my breed there. And then I can say my breed is equal to, let's say Sam's a husky now. I run this again. I still have a dog class, and if I take a look at my dog, if I hit tab, I only have breed. I don't have my breed available because my breed was just a parameter name we chose for the argument. So we said, oh, pass in the my breed argument, and I'm going to assign it to self.breed here. And I want to make this even more clear by saying breed is now my attribute. If I run this again, what happens is I pass in again my breed is husky, the type again stays dog, but if I say my dog tab, it's now my attribute, and it happens to be husky. So all we're doing here is you pass in the parameter or argument, and then it gets assigned to the attribute that you can later call on your object. However, by convention, you're just going to use the same parameter name for all three of these, which is why you end up seeing something like self.breed is equal to breed, and you pass in breed. This is confusing at first for beginners because they see breed in here 3 times, but you can tell that once you're familiar with object-oriented programming, it's just cleaner to have all 3 of these be the same term. That way you know what's being passed in and where it's being assigned. There's no real reason that they should all have those separate names. So right now, our dog only has a breed, but let's go ahead and give it more attributes. So what else could a dog have? Well, a dog could have a name. And maybe we can say, does the dog have spots or not? So we have a breed, name, and spots. So here we just say, create some more attributes. Self.name of the dog is equal to whatever name you pass in, and self.spots is equal to whatever you pass in for spots. And notice here, what I'm doing is I'm kind of expecting certain data types to be passed in. I expect breed to be a string, I expect name to be a string, and spots, the way I'm thinking about it, is actually going to be a Boolean. So let me have a comment here. I expect a Boolean, true or false, does the dog have spots or not? So hopefully you get the idea here that not every attribute you pass in is going to be a string, but it can be an integer, a floating point, it can be a list, it can be a lot of stuff. So I rerun this, and now let's take a look at what we need to define our dog. We need the breed of the dog, the name of the dog, and true or false, does it have spots? So we'll have the breed of the dog be a lab. We'll have the name of the dog be Sammy. And we'll have spots be false. Sammy doesn't have spots. So I run this. I run that again. I still have that dog class. But now when I say my dog and I hit tab, I see the options. I can see breed, name, and spots. So I can call these, check what the breed of that instance of the dog class is. I can check what the name of the dog is. And I can check, hey, does the dog have spots? And it'll tell me false. It doesn't have spots. One of the issues with Python being so flexible is that later on, when you're a programmer and expecting other people to use your classes, you're going to need to add in some documentation to let them know, hey, I'm expecting strings for breed, strings for name, and spots should be a Boolean. Because right now, I could say something like no spots, and Python's not going to complain here because I didn't do any sort of type check to make sure spots was a Boolean. So if I were to run this all again, there wouldn't be any error. Just when you say .spots, it would print out that string spots. Okay, so those are the very basics of attributes. We'll discuss better ways to have type control to make sure things like spots are Booleans later on in the course. But right now, what I really want to focus on is the basic idea that you use the class keyword, then with capitalized names, you define the name of your class, and the very first method in your class is going to be a special method called the init method. And this init method acts as a constructor, and we have this self keyword, which is a reference to the instance of the class. So that instance of the class is then going to have these dot attributes that you pass in based off what parameters you define up here. And by convention, the parameter name, the attribute name are the same, which means you will see it 3 times. Once when you pass it in, and then once here for the attribute, and once for the actual assignment call. Okay, those are the very basics of creating attributes. In the next lecture, we're going to discuss class object attributes, and then we'll move on to talking about methods. We'll see you there. Welcome back, everyone. In this lecture, we're going to be discussing object-oriented programming again, and particularly, we'll talk about class object attributes. And these are attributes that are going to be the same for any instance of the class, and then we'll move on to discussing methods, which are basically actions that you perform with the object you created. Let's jump back to the Jupyter Notebook where we left off last time. Okay, so here we can see our dog class that we created last time. And we also saw how the user could define various attributes. They could define the breed of the dog, such as lab or husky or golden retriever. They could define the name of the dog, Sammy, Frankie, whatever you happen to call your dog. And then we can define some sort of Boolean variable or even a string, whether or not it has spots. And here we saw we passed in the parameter as the user, and then it got assigned to the attribute over here. Now there may be attributes that are going to be the same for any instance of the dog class. For example, we know that it doesn't matter whether a dog has a certain breed, a certain name, whether or not it has spots, it's always going to be a mammal. So something we may want to do is have an attribute be defined at a class object level. Instead of having the particular instance always say that the dog is a mammal, instead we'll define an attribute above our init method here. So above this special method at the very start, we can define what's known as a class object attribute. And these are the same for any instance of a class. So let's go ahead and define a class object attribute. And what's special about these, since we know it's going to be the same for any instance of a class, we don't use the self keyword, because we know that the self keyword is a reference to this particular instance of a class. But since the class object attribute is the same for any instance of a class, we can just say something like the species attribute is equal to mammal. Now, as a quick note, if you're familiar with biological scientific classification, technically species is the wrong word to use here. It goes kingdom, phylum, and then later on class, and class is actually where mammal falls, but I don't want to end up accidentally using the class keyword twice here. So instead, we'll just pretend that the species of a dog is a mammal. Okay, so that's the side note for biology, but basically what we have here, back to Python, the class object attribute is going to be the same for any instance of a class. So let's test out this theory. I'm going to add this class object attribute. Again, note how I'm not using the self keyword because it's going to be true regardless of the instance. I rerun that cell, and if I call dog again and do shift tab, I still only need to define breed, name, and spots. So let's say the breed is again a lab. We'll say the name is equal to Sam, and spots, we'll say false, Sammy doesn't have spots. So I rerun this, now I have my dog ready to go. It's still a dog, and if I look at .tab here, I can see breed, name, and species. So species, even though we didn't define it, it's always available to us, and this is going to be the same, mammal, regardless of the instance of my dog. So it doesn't matter what I pass in for breed, name, or spots, because this attribute is not connected to self, it's not connected to any particular instance, so it's a class object attribute. And the way we format it is we have the class keyword, the name of the class, and then any class object attributes, and then you have your special init method for user-defined attributes. Okay, so those are the basics of attributes, mainly from the previous lecture for user-defined attributes, and then we have class object attributes. What I want to do now is actually discuss methods. Methods are essentially functions defined inside the body of the class, and they're used to perform operations that sometimes utilize the actual attributes of the object we created. So you can basically think of methods as functions acting on an object that take the object itself into account through the use of the self argument or self keyword. So what we'll do here is create our first method. So again, methods, unlike attributes, are more like actions. So these are operations / actions, and we can think of these formally as methods. And they basically look like functions inside of a class. And a lot of times beginners ask me, hey, what's the difference between a function and a method? Basically, a method is a function that is inside of a class that will actually work with the object in some way. So let's define DEF, and let's define an action for this dog to take. For example, maybe our dog could bark. And what we're going to do is say self, that way we connect this to the actual object so the dog can bark. And what's going to happen is when you call .bark on the actual dog instance, it's going to print something. And let's have it print woof. And let's go ahead and delete the name. Well, let's delete the spots attribute, so we're not dealing with so many attributes here. I'll delete spots here as well, and I'm going to rerun this. So we'll rerun this cell, and now if we take a look at my dog, shift tab here, it only needs the breed and the name. So let's define a breed for this dog again. We're going to say lab. Notice now I'm not bother passing the actual argument name there and just putting them in order. And then the next one was the name of the dog. So we'll have the name of the dog be Frankie. So I rerun this, and now I have my Frankie, which is a lab here, and the type is dog. And if we take a look at the species, it's still a mammal, and now the name of the dog is Frankie. So one of the key differences between attributes and methods is in the way we call them. Notice that attributes never had open and closed parentheses, and that's because attributes aren't really something that you execute. Instead, it's just something that's a characteristic of the object that you call back. So it's just information there about the actual dog. And I'm going to zoom out one level so we can see everything together here. So as I mentioned, for the attributes themselves, there's nothing to actually execute. Now for methods, that's a little different. And in fact, methods will need to be executed. So that means we need to have the open and closed parentheses when we do a method call. And I'll show you why. So right now I have my dog. And my dog is a mammal, it's a lab, and it's Frankie. And I want my dog to bark. If I just call bark right now with no open closed parentheses, you'll get back something that looks like this. And this basically says, hey, you have this method that's bound to your object, dog, at this location at your computer's memory. If you actually want to execute the bark method, you have open and close parentheses, you run that, and then you get back whatever the actual method does. In this case, it's just printing out woof. So that's how a method works. It's basically just an action that the actual object can take. In this case, it didn't really do anything besides the print statement, but usually methods are going to use information about the object itself. And we know that information about a particular instance of the object could be something like the name. So let's have the dog bark its own name. In this case, we'll say wolf, and here we're going to say my name is, and we'll use dot format here to pass in the actual dog's name. Now, a really common mistake that people do when they're first learning about object-oriented programming is they just pass in name. However, when we're working with objects, that's actually not good enough. What we need to do is reference the particular instance of the dog's name, meaning we need to reference not name, but self.name, because when you pass in name at the beginning, it gets connected to the object through the use of this self keyword. So here we need to say self.name, and that's going to, when you run bark, it's going to say print wolf, my name is, and it's going to say, hey, what is this dog's name? For this particular instance of the dog object, find its name. And it does that through the self.name call. And then we'll just insert it automatically because we only have one curly brace there. So we run that, and we're using print formatting there, which you can always review in case you're unfamiliar with this format call. Again, we'll say lab Frankie, rerun all of this to make sure that the bark operation has been set. And now, when we call bark, it's going to say woof, my name is Frankie. So it's able to actually reference things in the attribute sector. So you're able to say self.name and pass that in successfully into bark. Notice here how we call the self automatically. That way, in case we ever need to reference things, it knows what instance of the object it's talking about. Now, methods can take outside arguments. So we can pass it some other argument here. So we could say pass in some number. So what we could do here is when you call bark, you need to pass in some number. So we'll say woof, my name is blank, and the number is, and we'll say comma number. So note the difference here. I'm no longer saying self.number because number is already being provided for us when we actually call bark. So that means we need to actually pass in a number call. So I'm going to again rerun everything to make the changes to bark here. Rerun lab Frankie, rerun this, rerun that. And now my dog, if I hit tab here, it has bark, breed, name, and species. So what we're going to do is call bark. And if I just call bark like this, so let me zoom in very quickly. Let me delete the old line here. So if I just call bark like this, I'm now going to get an error. It's going to say, hey, bark's missing one required positional argument, number. So now this method is expecting some sort of added argument, number, because when this dog barks, it's going to say its name and the number you passed, because I'm passing it in here with number. Again, note here now I'm not using self.number because the user is provided that. It's not referencing some particular attribute for that instance of the class, like the breed or the name. So let's give it a number to bark for us. We'll say 10. Run that, and then it says, woof, my name is Frankie, and the number is 10. And those are the basics of using a method for a class. You say def, the name of your method. Notice now we're using lowercase, so it follows the conventions of a normal function call, except it's inside of a class. And then you pass in always the self keyword, and then you can work with other attributes by referencing them in a self.manner, or you can pass in new arguments that the user provides and reference those as well, no longer needing the self call because it's not connected to a particular instance of the class. It's just something that the user provides for you when they make the call. Okay, so we went over methods right now. I'm going to start a new class just to really drive the point home. So make a couple of new cells here, and I'm going to create a class called circle. So my circle class, let's give it a class object attribute. And remember, a class object attribute is something that should be true when you have any instance of the class. So for example, I know that pi is going to be equal to, more or less, 3.14, no matter how big a circle is. So I will set that as a class object attribute. So regardless of the instance of a circle I make, I will always be able to reference pi up here as 3.14. So now we create our init method. This is a special method. We always pass in self. So it's very common to forget that when you're first starting to work with objects, but you always pass in self. And now whatever we need to define a circle. So an argument we may need to define a circle is a radius. And just like when we learned about functions, we can actually provide default parameters here. So we'll define a default parameter of 1. So that's a default value for the radius. And I will say self dot radius is equal to the radius that was passed in. And then I'm going to make a method here. So now we have our method. And we'll say this method is called get circumference. And what this does is it has in self, so it can reference the particular instance of the object. And it's going to, no, I'm returning it. I'm not printing it out. I'm going to return the actual circumference of the circle. So if you do a little bit of math, you know that circumference of a circle is the radius of that circle times pi times 2. So 2 pi r is the circumference of a circle. I run that, and let's create an instance of the circle. So I can say my circle is equal to circle. And then when I call my circle here and hit dot, tab, I can have get circumference, and I can actually see here I have pi, and here I have radius. And I actually spelled circumference wrong, but let's actually fix that real quick. Circumference. Now I rerun this, rerun circle, hit tab, and now I see get circumference, pi, and radius. So let's call pi, see what happens. We get back 3.14, makes sense. It's a class object attribute. It's an attribute that's going to be the same regardless of what instance of the class. Then I'm going to say my circle dot, and let's call it radius, and it's 1. So why is radius 1? Because that was the default value I provided up here. What I could have done is provided another value for radius. Let's provide maybe 30 for radius here. And then it would have just overwritten default value. So then when I call radius again, after rerunning that assignment, I have 30. So you can have a default value here, and you can always overwrite it. Okay, so now let's see what happens when we call this method. We'll call my circle, and I will get the circumference, open close parentheses, run that, and it returns back the circumference. In this case, 188.4. Now those are the basics of methods, and I want to come back up here and show you a couple more things that you may consider when working with object-oriented programming. One thing to consider is that if you have an attribute, it doesn't necessarily have to be defined from a particular parameter call. So for example, I can create an attribute for the area. So a circle can have an area attribute, and I can say self.area is equal to the radius that's passed in times the radius that's passed in times pi. So pi r squared is the area of a circle. So I can say self.pi. And now I will have an area when I define the circle. So I can say circle 30, my circle.pi radius, and if I call my circle here and ask for the area back, I get back the area of that circle. The last thing I want to point out is because this is a class object attribute, I actually have two ways of calling it. I could say self.py because self references a particular instance of this object, or something people sometimes like to do is actually say circle.py if it's a class object attribute. So if it's a class object attribute, you can reference it in this manner, which is the name of the class and then the attribute, because you know this is going to be the same regardless of the instance of the class. So you may see it this way as well. And sometimes programmers prefer it this way because if you're reading someone else's code, it's very easy to see down the line, oh, this is a reference to a class object attribute. So it may be obvious here because our class is smaller, but you can imagine if we had hundreds of methods, instead of saying self.py here, it might be nice to say circle.py. That way when you're on line 101 or whatever it is, you can see here, oh, they're referencing a class object attribute at the very top of this class. So you run this and you'll get back all the same results. It'll all work exactly the same. So again, you can use self.py, or to really make it clear that it's a class object attribute, the name of the class dot the attribute name. All right, that's it for the basics of methods. Coming up next, we're going to discuss inheritance and polymorphism. We'll see you at the next lecture. Welcome back everyone to part 3 on our discussion of object-oriented programming. In this lecture, we're going to specifically focus on inheritance and polymorphism. And inheritance is basically a way to form new classes using classes that have already been defined. Let's jump to Jupyter Notebook and see how this works. Okay, so let's begin by talking about inheritance. And as we just mentioned, it's a way to form new classes using classes that have already been defined. And really important benefits of inheritance are the ability to reuse code that you've already worked on and to reduce the complexity of a program. So we'll start off by creating what's called a base class. So this base class is going to be called animal, and it's going to be a very simple class. In fact, its init method isn't actually going to take in any arguments. Instead, all it's going to do is print animal created. So we have a very simple class here. So for instance, if I made an instance of animal, it would just print out animal created because this init method gets automatically executed when you actually create an animal. Let's add on two more methods, one called whoami. And all this is going to do is print out I am an animal. And we'll have another method here called eat. And this is going to print out I am eating. Okay, so we can see that if we have an animal here, we can do dot tab and we can ask it to eat. So open close parentheses to actually execute eating and see print out I am eating. And the other one was who am I, and it'll report back I am an animal. This is going to serve as our base class. So newly formed classes can use the animal class in order to inherit some of its methods that you may want to use again. So for example, if I want to create another instance of the dog class, or actually recreate the dog class. So I'm going to recreate the dog class, but I start thinking, hey, a lot of the features and methods of my animal class are useful to a dog. For instance, dogs, they like to eat, so maybe I want to reuse some of my prior work in my new class. The way I can do that is by inheriting the base class, this animal class. So I'm going to pass in animal here. Before we weren't passing anything, but now if I pass an animal, I'm going to inherit or derive from this base class. So this is now known as a derived class because I'm deriving some of my features from this base class of animal. So I'm going to say dog inherits animal, and then in my init call, what I'm going to do is call animal dot underscore underscore init underscore underscore self. So I'm going to actually create an instance of the animal class when I create an instance of my dog class. And I'm able to do that because I'm inheriting from the animal class. And what I'm also going to do is print out dog created. So let me run that, and I'm running that with Alt-Enter so I can get a cell right below. So I have my base class of animal, and then I have my other class of dog, which is now going to inherit the methods of the animal because inside my init method, I called animal.initMethod self. So now let's see this in action. I'm going to say my dog is equal to dog, and I run this, and now I see that an animal is created because when I run this line of dog, this init method gets called, which in turn runs the init method off animal, which in turn prints out animal created, and then after that's created, I print out dog created. But here's where it gets interesting. All those old methods that were available for the animal, who am I and eat, are now available for my dog. So even though inside this dog class, I don't have eat or who am I defined, I'm still able to use them because I was able to derive them from my base class of animal. And that's the main idea behind inheritance. I can now reuse methods that should be common between classes by just inheriting. So I don't need to rewrite all these methods for my new class. Now you may be wondering, well, what if I want to overwrite one of the older methods? Well, that's actually no problem. All you need to do is say def in your new class, and then just make sure to use the same name as the old class method, such as who am I. And now, instead of saying I am an animal, we're going to print out I am a dog. So rerun this to make sure we've redefined it. Rerun my dog, and it still says animal created, dog created. I can still call eat, but now when I call my dog, who am I, it says I am a dog. Before, it would have said I am an animal. So let's test that theory. I'm going to delete this, who am I, rerun this. We'll create our dog again, animal created, dog created, eat. And if I say who am I, notice I didn't overwrite it this time. It'll just say I am an animal. So you're able to overwrite the previous methods of your base class in case you need to. You're also able to add on methods. So, we're going to say def bark self, and then print out woof, so we can add methods and we can overwrite. So let me copy this eat method here and paste it in. And now I'm going to say I am a dog and eating. So I run this again. I recreate the instance of my dog here, animal created, dog created. And now if I call eat, it says I am a dog and eating because I overwrote the original method. I can still call who am I because I inherited from that base class, and it says I am an animal because I no longer overwrote it here. You can add in the method again call and then rerun this. But now I also have bark. So I could say my dog, bark, and it will print out woof. The main ideas here is that all you need to do is inherit from your base class, and now you have access to all these old methods that you wanted. And if you ever want to overwrite them, you can just overwrite them as so, recall that same method name, and then do whatever you want there, and you can always add in more methods. So that's how inheritance works, and let's move on to discussing polymorphism. So we just learned that while functions can take in different arguments, methods belong to the objects they act on. Let's finish this lecture by talking about polymorphism. In Python, polymorphism refers to the way in which different object classes can share the same method name. And then those methods can be called from the same place even though a variety of different objects might be passed in. The best way to explain this is through an example. I'm going to create two new classes. I'm going to redefine my dog class, and then I'll also create a similar cat class. We'll say def init, and the dog just takes in a name, so you can name your dog. So we assign the dog's name attribute to the name that's passed in, and then the dog is going to be able to speak. And in this case, when it speaks, it's just going to return its own name, so self.name, plus we'll say says woof. So when the dog actually speaks, it reports back whatever name you assigned it, and then says woof. And I'm going to copy this, make sure I run this cell, and right below it, I'm going to create a very similar cat class. Same deal if it's init method, you provide it a name, but instead of speaking says woof, we're going to say speak says meow. So almost the same class, except the cat says meow and the dog says wolf. Okay, so I'm going to zoom out so we can see a little more of our code. We've defined the dog class and the cat class. Now let's create two instances of them. We'll say Nico is a dog with the name Nico, and we'll say Felix is the variable name for a cat with the string name Felix. So I'm going to print out what happens when Nico speaks. So Nico says wolf. Looks like I forgot a space here, so let's clean that up a little bit. Rerun these two cells. Nico says wolf, nice. We have a little space there. And then have Felix also speak. Notice here I'm actually executing speak with open close parentheses, and Felix says meow. So here we have a dog class and a cat class. Each of them has the speak method. When called, each object's speak method returns a result that's unique to the object. That is to say, it's unique for the dog to say wolf, and it's unique to the cat to say meow, as well as their names are going to be unique to that particular instance of the class. Now there's a few different ways to demonstrate polymorphism. One of them that's pretty simple is with a for loop. So I can say for pet class in, and now I'm going to say Nico and Felix. And what I'm going to do is I'm going to iterate through this list of items. And I want you to notice something here. I'm going to say print the type of pet class. And in fact, I'm just going to say pet, so that way I don't confuse you. So we'll say for every pet in this list, print what type of pet it is. So what type of class it is. And then also print what happens when you say pet.speak. So I run this, and this is an example of polymorphism. So both Nico and Felix share the same method name called speak. However, they are different types here. So notice we have main dog and then main cat. And let me remove this type call. They're both returning a string, but it then should be noted that one of them is saying wolf and one of them is saying meow. So another way to show this, besides iteration, is through a function. And this is probably the more common way to see it being used. And I can say def pet speak. So this takes in some pet. It doesn't really care if it's a dog or a cat, because what it's going to do inside of the function is just take that pet object and then call it to speak. So notice when I say Nico pet speak, it says Nico says wolf. And if I were to pass in Felix to pet speak, it would say Felix says meow. So pet speak itself doesn't actually know whether you're going to pass in a dog or a cat. Remember, these are two different classes, and they are pretty similar in our case, but they could technically be wildly different. Dog could have 100 methods, cat could just have these 2 methods, but they share the same method name speak, which means I can leverage that capability by happening to either iterate through a list of these different classes and happen to call the same method name, or most likely I pass it into some function where later on it calls that method called speak. So in both cases, we're able to pass in different objects and we obtain object-specific results from the same mechanism, that same method call. Now, a more common practice is to use abstract classes and inheritance. And what an abstract class is one that never expects to be instantiated. You never actually expect to create an instance of this class. Instead, it's just designed to basically only serve as a base class. So we're going to say the animal class again. And the animal class is going to have an init method that takes in self name. This is the constructor of the class. And we're going to assign animals the attribute name based off what's passed in. And then this base class is going to have speak. However, later on in our code, we never actually expect to say something like my animal is equal to an instance of animal. In fact, this animal class is never actually expected to be instantiated. I don't expect to ever make an instance of the animal class. Instead, this is basically to be only used as a base class. So this speak method, and this is really common with polymorphism as you get into more advanced object-oriented programming, what we're going to do is raise an error. And we're going to learn about errors and exceptions in the next section of the course. But essentially what's going to do is say, hey, we have some sort of error here. So we'll say not implemented error. And we'll say subclass must implement this abstract method. So we run this, and what's going to happen is if we actually create an instance of animal, something which we're not expecting to do, so we'll say Fred is the name of this animal. If I say animal speak, I get back, hey, not implemented error. And this is actually telling me, hey, you're supposed to use a subclass to implement this abstract method. So the reason this is an abstract method is because in the base class itself, it doesn't actually do anything. It's expecting you to inherit the animal class and then overwrite the speak method. So I could delete this line because, as we just said, we never actually expect to use animal in that fashion. Instead, what we expect you to do is call dog and then pass in animal as you construct this dog class. And now you no longer need to have this sort of init method here. Instead, what you can do is say def speak self and then return self.name plus says woof. And we'll do the exact same thing for cat. So I'm going to copy and paste this. And then instead of saying dog, we'll say cat there. And instead of saying wolf, we'll say meow. Run that. I will say Fido is equal to a dog with the name Fido. And I will say Isis is an instance of cat with the name Isis. And now I can print out Fido speak. And now I can print out as well Isis speak, where Isis says meow. Okay, so some real life examples of polymorphism, since these are really basic examples of using the same method name and then also having these abstract methods, is maybe opening different file types. So you may want to have the method name called open, which makes sense. You're going to open a file. But there's lots of actually different files. There's Word files, PDF files, and Excel files. And if you were trying to make a class that could be a base class for opening files, and then you have other classes that would inherit that, maybe a class for opening CSVs, another class for opening Excels, another class for opening Word files, you'd want them to be able to share the same method name, the .open name. So that's a more realistic example, and that's an example of polymorphism, where you can have some function, maybe a general open file function, can take in any of those classes that you have and just call .open on them. And it's up to the class itself to decide what actual type of file is being opened. Okay, so that's polymorphism. Basic idea is you have these two separate classes that happen to share the same method name, allowing you to then call those same method names without needing to worry about the specific class that's being passed in. We'll finish off our entire discussion of object-oriented programming in the next lecture, where we finally go over special methods. We'll see you there. Welcome back, everyone. To finish off our series of lectures on actually working with object-oriented programming in Python, we're going to talk about special methods. Special methods allow us to use some built-in operations in Python, such as the length function or the print function, with our own user-created objects. To get an idea of how this all works, let's jump to a Jupyter Notebook. Let's start off with a simple example. I'm going to create a list, 1, 2, 3, and then let's say I wanted to check the length of my list. Well, I could just call len on my list. What if I wanted to check the length of one of my own objects? So to show you what's going to happen is if I create my own sample class, and it's a very simple class, we just say pass here. I create an instance of my sample, and then try to check the length of my sample. What's going to happen is I get a type error. Object of type sample has no length. And maybe I want to try to print out my sample. So I say print sample, and I just get back the report of where my sample object is located at my memory. Unlike my list, where if I tried to print it out, I would actually get back my list in a string form. So the question arises, how am I able to actually use built-in Python functions such as length or print with my own user-defined objects? And this is where those special methods come into play. So special methods, some people also call them magic methods or dunder methods because they use double underscores, work in the following manner. And there's more special methods than what we're going to show here, But for now, these are the main ones you're going to be using. I'm going to create a book class, and we'll say init, and init was the first special method we learned about, and it's special because it's basically called automatically when you create the object. So our books are going to have a title, an author, and pages. And what we're going to do here is say self.title of the book is equal to the title you pass in when you create it. The author attribute is equal to the author you pass in when you create it. And then the pages attribute is equal to the pages that you pass in when you create your instance of your book. And let's imagine I wanted to print out my book. Right now, if I say B is equal to book, where the title is Python Rocks, let's say the author is Jose, and it has 200 pages. If I try to print my book, it just says, hey, you have this book object in memory. What happens is when you call the print function, what the print function does is it asks, what is the string representation of B? So if I try to cast or transform B into a string, what happens is I just get a string version of this report when I print it. Instead, what we can do is actually use the special method related to that string call, which is underscore underscore str underscore underscore. And what this does, if there's ever any function that asks for the string representation of your book class, then it's going to return whatever this method returns, which is why it's a special method. And make sure you use return here, not print. And I'm going to return whatever I want to be printed out. So when I print out a book, it might make sense to kind of print out a lot of things. So we'll use an f-string literal format. I will say self.title by self.author and shift enter here. So what happens is when I'm going to call the print function asks the book object, hey, do you have a string representation of yourself? To which the book object then says, yes, I do, because I have this special str method, and I return this string. Where the string, using f-string literal formatting, I can actually pass in self.title, so it grabs this title, and self.author, so it grabs this author. So let's rerun these cells. And now if I say print B, I get back Python Rocks by Jose. So if I ask for the string representation, it's the same thing, because the print function, all it does is it prints out what string representation returns back. So that's the special method for strings and printing in general. Next, we can do the same thing for length, because right now if I try to check the length of my book B, it says, hey, object of type book has no length. So as you may have guessed, the special method that goes along with this is len, and we're going to say self here, and then we can return back whatever we want to be printed out when you ask for the length of the book. And here, it probably makes the most sense to just return back the number of pages the book has. So we'll return back self pages. I rerun these things, and when I print these books out and ask for their length, I get back 200. Finally, what we could do is, let's say we wanted to delete a book. What you can do is you can call the keyword del, space, and then pass in the variable name, and that will actually delete that book from the memory on your computer. So if you ask for B again, it's going to say name error, B is not defined. So this is a way to delete variables from your computer's memory. Sometimes you may want to print out a report upon deleting the variable, or you may want other things to occur when you delete the variable. In order to basically specify extra things that may occur when you call delete, you can use underscore underscore del underscore underscore self, and then we can add certain things to happen when you actually delete an instance of the book. So I will say print a book object has been deleted. And then I will say shift run here, or shift enter. Let's define our book again, and let's print out the book. I'll do alt enter here to get some cells below. So I printed out my book. Let's check to make sure the book still exists. Print B, and then to delete the variable, I can say del B. And now when I run this, I get out the extra statement, a book object has been deleted. So when I call B again, it's now deleted, B is no longer defined, and I was able to add a print statement to maybe give the user more information when they use the special del keyword. All right, those are the main special methods that you're going to be using as you're just starting off with Python. You can check the documentation for many more dunder or special or magic methods, but really these are the main ones you're going to be using, especially str and len. So again, str, it returns back the actual string representation, so you can print out user-defined objects. Len returns back the length, so you can return back the length of user-defined objects. And that ends our discussion on object-oriented programming. Let's now test your skills with a homework assignment and a small challenge project. Welcome back, everybody. Now that we've gone over a series of lectures showing you how to work with Python for object-oriented programming, let's test your new skills by giving you a quick homework assignment. I'm going to go over the notebook that contains this homework assignment. Alright, so here I am at the GitHub repo just to show you where the notebook is available. If you go to Complete Python 3 Bootcamp under the Object-Oriented Programming folder, you can find the Object-Oriented Programming Homework notebook. And it's the notebook that's right after that main lecture notebook about object-oriented programming. And this homework assignment has two simple problems. If you recall, during the lectures, we created a circle object, so we could create instances of a circle, and that circle object had a radius. So what you're going to be doing is something similar. We're going to use geometry to create two different objects. We'll have a line object and a cylinder object, or a line class and a cylinder class. Let's go over the first one. So here we have three methods for you to fill out. One is the first special init method. The second is the distance method, and the third is this slope method. So what we expect to be able to do is given two coordinates in the form of a tuple. So we have xy coordinates, coordinate 1 at x equals 3, y equals 2, coordinate 2 at x equals 8, y equals 10, or really whatever numbers. You'd be able to pass in those coordinates, remember they're tuples, and then using that, you'd be able to call the distance method to get back the distance between these 2 points, and the slope method to get the slope between these 2 points. And you can just Google around for the actual formulas for distance and slope, but in case you want to pause your screen real quick, here's the actual distance formula given 2 points. So it's just x of 2 minus x of 1 squared plus y of 2 minus y of 1 squared, and then take the square root of that, where you have y2 and x2 are 1 point, and then x1 and y1 are the other point. So that's the distance formula. And the slope formula, as you may recall, is just y2 minus y1, x2 minus x1. So these are the formulas that you're going to be using, and you're going to take in these coordinates and convert those formulas into method calls here that end up basically returning the result of that formula. And then we have problem 2, which is quite similar to that circle class, except this time it's a cylinder. So what you need to do is, again, fill out this form right here to set the attributes, and then have volume method filled out and surface area. And you can always Google search the Wikipedia page for a cylinder. They have the formulas for the volume and surface area of a cylinder there. So an example output is given a cylinder with a height of 2 and a radius of 3 units. Pass the volume method to actually get a volume back, and then execute the surface area method to get the surface area. And that's basically it for this quick homework assignment. I would say go with problem 2 first, actually, because it tends to be a little simpler than the line class, in case you want a more gradual pacing. Okay, we'll see you at the very next lecture where we go over the solutions. Best of luck, and remember that the coordinates here are being passed in as tuples. We'll see you at the solutions. Welcome back, everybody. Let's now go over the solutions for the homework assignment from the previous lecture. Alright, so here we are. We first had the line class, so let's start with that one. Remember that we're taking in these coordinates as tuples. So there's lots of different ways you could have done this. One way is to create the two coordinates as attributes. So we could say self.coordinate 1 is equal to the coordinate 1 that's passed in, and then self.coordinate 2 is equal to that second coordinate that's passed in. So this is one way to do it. And then later on, what you do is just tuple unpacking to grab the individual components of these tuples. So for example, in the distance formula, we know the distance formula at the end of the day should look something like this. It should be x2 minus x1 to the power of 2, and then we'll say plus y2 minus y1 to the power of 2, and then this whole thing squared. So one way to do that is just to the power of 0.5. So that's one way to take the distance formula, and in order to get x2 and x1, what we could have done is just tuple unpacking here. I could have said x1, y1 is equal to self.coordinate 1, and then x2, y2 is equal to self.coordinate 2. So you could have done it this way. The other approach you could have taken is just right off the bat, when you actually create attributes, is create an attribute for each of these. So you could say self.x1 is equal to coordinate 1, and then maybe use some indexing here. It's really up to you what approach you want to take. The main idea being that eventually you have to realize you need to somehow extract the actual components of that tuple, either through indexing or through tuple unpacking. And this is something that I wanted you to get practice with, because often you're not going to just pass in single variables into your argument calls. They may be something like a list or a tuple, so you should have classes that are able to work with that. Finally, let's have the slope equation. And we can just copy and paste these lines from up here. And then for the slope, we just return rise over run. So rise is y2 minus y1. And then we're going to divide that by x2 minus x1. We'll run that, and then let's check this out. So we'll say c1 is equal to 3, 2 coordinate, c2 is equal to 8, 10 coordinate. I'll create my line object and pass in c1 and c2 here. And now I'll check out the method calls. We'll say distance, open close parentheses, because we execute that. And that looks like it matches up. And then we say my line, check the slope. It looks like that matches up as well. If you're getting different numbers for distance and slope, given these two coordinates, double check your actual equations here. You may have mixed up x1 and x2, or y2 and y1. So keep that in mind. These should be the results you get for distance and slope given these coordinates. So definitely check your math if you're not getting those same results. It's really easy to make a typo here or use parentheses in the wrong way. So just keep that in mind as you continue. Now we're going to move along to this cylinder class. So as I mentioned when we were going over the homework, this one's actually a little simpler than that line class. So here we have height and radius. Notice they have default height and radius. What I'm going to do is make those both attributes straight up since they're integers being passed in. So self.height attribute is equal to height, and then the instance's radius is going to be equal to the radius that is passed in. And then we're going to just return the volume equation. The volume for a cylinder, you could have Googled this. It's basically just height times pi. We could have also done a class object attribute there, but I'll just pass in 3.14. And then it's going to be the radius. So self.radius to the power of 2. And notice here how I'm using self.height and self.radius inside these method calls, because I need to reference the instance of the object's own height and own radius. I can't just reference height and radius by itself. I need that self parameter. Then for surface area, this one's a little more complicated of a formula. Basically, you have the top and bottom of the cylinder, which is pi r squared. So I'm going to say that the top of the cylinder is pi r squared. So self radius to the power of 2. There's a top and bottom, so for the whole surface area, I'm going to return 2 times top, 1 for the top, 1 for the bottom, and then plus the rest of the formula, which is 2 times pi times self.radius times self.height. And the formula is basically just grabbing that middle section of the cylinder and then flattening it out so you actually get a rectangle. Okay, so that's surface area. Let's run this and make sure that our results match up. So I'll say my cylinder, or my cyl, call the cylinder right here, 2, 3. We'll say c.volume. And it looks like I have an error, name C, whoops, my cylinder, not C. 56.52, perfect. And let's check out my cylinder surface area. Run that, and we have 94.2. Okay, so this should have been pretty straightforward, especially because it's very similar to the circle class. If you're having any issues on this, or there's something that's confusing to you as far as creating these methods, please post to the Q&A forums, and we're happy to give further explanation. I'm going to give a quick overview of what we just did here. So let's start with the line class. First thing we have to realize is that these coordinates are being passed in as tuples, and you have various options of how you want to work with these here. Either you can do the unpacking in your actual attributes, so then you can have self.x1, self.x2, and so on, or once you assign these coordinates, you can do the unpacking in the methods themselves. Again, totally up to you. Then just make sure that you're applying these equations correctly for both distance and slope. For the cylinder, it's a very similar thing. We assign the attributes height and radius, and then we just return back the actual mathematical formulas for volume and surface area of a cylinder. All right, thanks everyone. Again, if you have any questions, post to the Q&A forums, and we're happy to help you out there. We'll see you at the next lecture. Welcome back, everybody. We just had your homework assignment for object-oriented programming, where we had two geometric classes that were basically structured, and you just had to fill in a couple of lines in the attributes and methods part of that class object. Now for your challenge, it's going to be a little more free-form, and we're going to have you create a bank account object with a couple of attributes and a couple of methods, as well as some important special methods and self-checks. So let's go to the challenge notebook and explain what we expect you to do. All right, so here I am at the repo, and this should be the same if you've downloaded the notes, but under the Object-Oriented Programming folder, you should be able to find the OOP challenge. And in this Object-Oriented Programming challenge, we're going to want you to create a bank account that has two attributes, an owner attribute and a balance attribute. And then there's going to be two methods for that attribute, deposit to deposit money to your bank account, and withdraw to withdraw money from your bank account. And as an added requirement, withdrawals may not exceed the available balance. So for this withdraw method, you're going to have some sort of if statement to check, are you drawing too much? So here, we basically only have class account and then pass. So this is a little more free-form because it's going to be up to you to fill out the init method, the deposit method, the withdraw method, and then the owner and balance attributes. So once you instantiate the class with an owner, which is going to be a string, the name of the owner, and some current balance, so some initial balance for the account, you should be able to print out the object. Recall that there are special methods, specifically the str special method, that allows you to print out whatever you want when you call print on your object. So in this case, I have the account owner and the balance. You don't need to format your str method exactly like this, but you should be able to report back some useful information. Then you should also have the owner attribute, in this case the owner is Jose, and the balance attribute, in this case the current balance is $100. Then you can make a series of deposits and withdrawals. So the deposit 50, we deposit and actually add in $50 to the balance, so that should affect the current balance. And then we should be able to withdraw money, and we see withdrawal accepted, so we withdrew $75 from the balance. Now if you make a withdrawal that exceeds the available balance, in this case we try to withdraw $500, you should be able to see funds unavailable as the output. Okay, so that's your challenge for this object-oriented programming assignment. And I quickly want to touch upon this idea of being able to call methods that affect attributes. We haven't truly seen that yet, so I want to show you a very simple example. I'm going to create a class, and this is going to be a simple class, so I'm just calling it simple. And the init method, all we're going to do is say some value here. And we'll say self.value is equal to the value passed. And then I'm going to have a method called add to value. And this will be self. And then some amount. And what this does is it takes in the current value of self, or current self.value, and then it says self.value plus the amount. And this is something that we haven't really done before, because notice here, this method actually doesn't return anything. All it does is it takes the amount that's passed in, and then it adds it to the value. So this is kind of a hint of what you're going to need to do in your bank account class. So I'll say my object is equal to an instance of simple, and we'll say that the current value is 300. So when I call my object value attribute, I get back 300. You can kind of think of this as akin to the balance of the bank account class. And if I say my object and I call add to value, let's say add another 500 to my value, notice nothing is returned. Because all that's happening when you call this method is it takes in the amount you passed in. Here it's 500. It grabs your current value, notice the self call, adds the amount to it, and then reassigns self.value to reflect this change. So now when I call in my object value, it's 800. Okay, so that's basically the little example I wanted to show you of how you would actually grab a current attribute and then affect a change on it. And it's up to you if you want to print something like, we just added curly braces to your value, and then you could say something like .format amount. So if we rerun this, I would then get back an actual printed message here, just so I know that it's actually working. Okay, best of luck on that challenge. Again, it's definitely more free form because we want to push you to that next level where you're able to break down a concept into code. If you have any questions, feel free to post to the Q&A forums. In the next lecture, we'll go over an example solution. We'll see you there. Welcome back, everybody. In this lecture, we're going to go over an example solution for the OOP challenge. Remember, for this more open-ended project, your solution will probably vary than the one shown here, but as long as you're able to get the same results, it should be okay. Let's go to a Jupyter Notebook now. Okay, so let's begin by creating our account class. And I'm going to start off with the init method. We'll say self as always, and we know there's two attributes that are going to be defined here, the owner and the balance. And if we wanted to, we could set a default balance to be set equal to 0. That way we only need to provide the owner. That's optional. And we'll say owner is equal to the owner that's passed in. And we'll say the balance of this instance is equal to the balance that's passed in. Next, what we're going to do is set up our deposit and withdraw methods. So we'll say deposit self, and we're going to need some amount to deposit. So we'll say deposit amount, or dep underscore AMT for short. And what we do here is we grab our current balance and we'll set it equal to our current balance plus that deposited amount. And then what we can do is instead of returning anything, we can just print out added blank to the balance. And we can use f-string literals if we want here, or .format, whatever you prefer, and then just pass in the amount. Now for the withdrawal, it's going to be a little different because remember the withdrawal should check whether or not you have enough funds. So that means we're probably going to need an if statement here. So we'll say withdrawal amount, and we'll say if self.balance is greater than or equal to the withdrawal amount, then self.balance is going to be equal to the current self.balance, and I'm just using tab to autocomplete here, minus the withdrawal amount. And then I'm going to print out withdrawal accepted. Else, that means that the balance is less than the withdrawal amount. I'm going to print, sorry, not enough funds. Then after all of this, I want to be able to print out my account object. So I will have the special str dunder method. It'll just take in self. And here we can decide what we're going to return. It's really up to you, but in our case, I'm going to return the owner. So we'll say owner is curly braces, balance is curly braces. And if we wanted a new line to be printed, as we did in the example, we could say / new line. And then you can either use .format or string literals. If you wanted a string literal, you just put an F there and then pass in the information. So in our case, it's self.owner, and for the balance, it's self.balance. Okay, so remember, you need to return that for the string function. You don't just print it out. And let's try to create an account here and see if we get any errors. We'll say Sam is the owner, and Sam's going to have 500 as their balance. So let's check that we can grab the owner. Sam's looking good. Let's check that we can grab the balance. 500, that's looking good. Now let's see what happens when we print out A. We get owner Sam, balance 500. Let's make a deposit. So I'm going to make a $100 deposit. Added 100 to the balance. Let's print out A again, make sure that the balance has been affected. Great, now we see 600 there. Let's make a withdrawal. A withdrawal of, let's do 600 itself to empty out the account. So that worked out. We'll print A. Our current balance is 0. Now if I try to do one more withdrawal of anything, I should get an error because I have a balance of 0. Or at least I should get a print statement. Okay, sorry, not enough funds. And if I print out A, we can confirm that I have 0. All right, that's all you had to do for this project. Let's do a quick little overview. We set up our attributes so that the instance of owner and balance were equal to whatever you passed in here. We have a simple deposit method, and as a quick note, for these actions of equal to the same thing plus, what you could do as an alternative is instead of writing equals self.balance plus, is just say plus equals. And it's the same thing over here. You could have just said minus equals. So this is kind of sleeker, but it's up to you what's more readable. So you could have done that for the deposit and withdrawal methods. Remember, the withdrawal method needed to have an if statement in order to check that we had enough money in the balance. And then for the string method, we just return back really whatever you want, as long as it conveys the information of the owner in the balance. Okay, you can check out the solutions for more information, and if you have any questions, post to the Q&A forums, and we're happy to help you out there. We'll see you at the next lecture. Welcome everyone to the section on modules and packages. In this lecture, we're going to start off by talking about PyPy with pip install. PyPy is a repository for open source third-party Python packages. And if you've worked with other programming languages, it's similar to RubyGems in the Ruby world, PHP's packages, CPM for Perl, and NPM for Node.js. So far, we've really only used libraries that come internally with Python. And these are known as the standard library or the built-in libraries for Python. Things like the math library. Now there are many other libraries available that people have open sourced and shared on PyPy, and these are also called packages. And we can use pip install at the command line to install these external packages. By installing Python from python.org, or by installing the Anaconda distribution, as shown earlier in this course, you actually have already installed pip. And pip is a simple way to download packages at your command line directly from the PyPy repository. Now there are packages already created for almost any use case you can think of. Python is a hugely popular language and it's growing very quickly. So that means if you ever want to work with Python with some other external use case, maybe you want to make web development with Python. So you would Google around and eventually discover that there's libraries such as Django or Flask for web development with Python. Or maybe you have a more specific use case like working with PDFs with Python or working with Excel documentation with Python. In that case, you can always do a quick Google search, and almost always the links that come up first are either the PyPy page for the package or the package documentation. And we'll show you a little exercise of what a good Google search looks like. So what we're going to quickly do now is show you how to download and install external packages. To do this, we'll open up our browser, but we're also going to be working at our command line. So remember, for Windows users, that means open up your command prompt, and for macOS and Linux users, that means open up your terminal. So let's have a browser open along with our command prompt. Okay, so here I am at my command line, and let's show you how to install a package that's hosted on PyPy. Something you do need to be aware of is that your firewall may block pip from accessing the internet. So if you're on a work network or you're on a work computer that you don't have full admin permissions, you may need to check that or talk to your network administrator. But let's move on. And what we're going to do here is type pip install space, and then here's where you would actually put in your package name. So there are a ton of packages out there. We're going to start with a package that you may already have installed because you've installed Anaconda, and that's the request package, which allows you to request information from websites online. So this is just a general syntax of how you would download a package. Notice here, I'm typing this directly into the command line or directly onto my terminal or command prompt. I'm not actually calling Python first. This is a command line utility. So you hit enter here, and you may get the requirement already satisfied. Most likely, if you installed Anaconda, you already have requests installed. So this is what it looks like when you already have it. What I'm going to show you now is a library that you most likely do not have yet, and that's the Colorama library. And this is just a bit of a silly library that allows you to print out colorized text at your command prompt or at your terminal. So type pip install Colorama, notice the spelling here, hit enter, and we actually already have it installed because I ran this line already. So what we're going to do now is run the actual Colorama external package that we just installed. So what I'm going to do now is type Python, and let's try checking out Colorama. So to do this, it's actually quite simple. All you need to do is say from Colorama import init, And then on the next line, call init. So basically is a bit of an initialization function that allows you to set up depending on what platform you're using. And then what we can do is say from Colorama import. And what we're going to do here is say import fore, so that's capital F-O-R-E, which stands for foreground. And then I will create a print statement that says for dot, and then in all caps red, plus, and I will just say some red text, and then hit enter. And now you see I have red text. And we can do that for a variety of colors. So I can say now print for green plus switch to green, and now we've switched to green. So again, just a very simple library that allows you to incorporate color directly at your command line. This is not a library we will ever really be using again, but it's just something fun that you can play with. And you can check out the documentation simply by Google searching Colorama. What I want to show you now, let me quit out of this Python session, is show you how you would actually create a Google search and what kind of things to expect to pop up when you're looking for an external package that you may not know ahead of time. So for example, let's try to solve the problem of trying to work with Excel files in Python and figuring out a package that allows us to do that. So when you're looking for a Python package for any particular workflow, it's always best to start with just a simple Google search. And I know hopefully this seems pretty obvious, but a lot of times the best thing to do, and pretty much everybody does this, no matter how experienced a developer they are, is you just Google search Python package for, and then whatever they're looking for, whether it's Excel, for PDFs, and you should always end up seeing in the top results some sort of link to helpful information. So let's start off with the example for Excel. And as we scroll down, we'll eventually see python-excel.org. And if you click on that link, it actually reports back a bunch of packages that are available. OpenPyXL, XLRD, XUtils, a ton of stuff that you can play around with. So then what you end up doing is you either go to the documentation or you go straight to the download link. And typically when you go to the download link, it takes you to the Python Software Foundation website for PyPy, so pypi.python.org. And here's just official information about the actual package. Depending on how big the package is, if it has more users, it almost always has a separate documentation page, and the documentation will be linked somewhere in the top few lines. So you click here on package documentation, and it will take you to the official documentation for that actual package. And a lot of times they're hosted by readthedocs.io. So now here we see some nice documentation, and what we can do is figure out how to install it from this documentation, or typically what you end up realizing is it's always just pip install and then the name of the actual package. So we know that it's OpenPyXL. Let's now go back to our command line and install it. So then here, back our command line, what we're going to do is say pip install OpenPyXL, hit enter, and I've actually already run this before, but that's how you would install a package from the internet from PyPy. And then later on, you could call Python, and then you should be able to import OpenPyXL with no issues. That's the basics of using pip install with Python and figuring out what external packages are a good fit for you. Hope that was useful. If you have any questions, feel free to post to the Q&A forums. Coming up next, we're going to learn how to create our own modules and packages using Python. We'll see you there. Welcome back, everyone. In this lecture, we're now finally going to discuss how to write your own modules and packages. So we understand how to install external packages that people uploaded to PyPy. Let's explore how to create our own modules and packages. And to clarify some of the semantics here, modules, it's really just a .py script. So it's a fancy way of saying, here's a .py script that I'm using in another .py script. So that act of using it in another .py script allows you to call it a module. Again, this is really just semantics, but packages are then a collection of modules. However, there's a key .py script called __init__.py that needs to be placed inside of a folder to let Python know that this collection of .py scripts should be treated as an entire package. So we're going to show all of this through some examples. Keep in mind, since we're dealing with .py scripts here, we're not going to be able to show these examples through the notebook. Instead, what we're going to need to do is use Sublime Text Editor or any other IDE that works with .py files in order to create the scripts and folders. Let's get started by opening up Sublime Text Editor. All right, so we're going to start off by creating two files here. The first one, we'll save it to the desktop. We'll say File, New File, or we can actually save the one we currently have, Save As, and on my desktop, I'm going to save this as my module.py. So this is the module, and remember all that a module is just a .py script being called in from another file. So let's create that other file. We'll say New File, and this one, we're going to save it also on the desktop in the same location as my module.py, and we'll say my program.py and save that. So inside my module, what I'm going to do is just create a very simple function. We'll say def and then say myfunc, and all this does is it prints out, hey, I am in my module.py. Control S to save that. And then in my program, this is another .py script, and I want to use the code from my module. So here we can get the idea that if you have a really large script, you're not going to put everything in one giant .py file. Instead, it will be nice to split it up between multiple .py files, which means just split it up between different modules. And then later we'll see how we can aggregate a bunch of modules to create a package. So far, what we're going to do is in my program, say from my module import, and then we're going to import my func. And let me make sure I spell that right. Okay, my_func. And that means I can now call it here. So we'll say myfunc. I'm going to save this, and let's see if it worked by going to our command line. So here I am now at my command line. Remember, I saved these files at my desktop. So let's cd to the desktop, change directory. And now I should be able to call Python, and then call my program.py, hit enter, and I see, hey, I am my module.py. So we were able to successfully call the other function from the other module.py file into my program.py. And this is the very basic way of how you would actually format .py scripts in order to not have everything in a single script. Now at a certain point, even this is going to start to be too much, and now you're going to want to aggregate modules together to form a package, and that way you can have different folders for different packages. So let's now show you how to create a packages. So we're going to come back here to my program.py and my module.py, and we'll open up and say new file, and then we're going to save this, save as, and here at my desktop I'm going to do a few things. The first thing I'm going to do is create a new folder here. In this folder, we'll call it my main package. Hit enter. And then inside of this folder, we're going to create another new folder, and we'll call this sub package. So we're going to be creating lots of files and folders here. So right now we have at my desktop my module.py and my program.py, and I've also created my main package folder, and inside of that I have my sub package. Now, since these are just directories or folders, we need to let Python be able to understand that we want to treat these directories not just as a normal directory, but as an actual package. So to do that, inside both my main package and sub package, I'm going to have to create a file called __init, __.py. Save that, and make sure you have this init py file in your package. Now, you don't actually need to write anything in this file. It just needs to be there so that when Python goes searching through these packages, it understands that it's not just a normal directory, it's an actual package. So we're going to create one more file. We'll say new file, and we're going to save this. Under sub package, we'll create another __init __.py file. And again, this one's going to be blank as well. So we have both of these. Notice here how Sublime's telling us which one we're referring to, this one in main package and this one in the sub package. So we're going to close these. We're not going to be working with them anymore. We just need to have them named there. Okay, so I have my module and my program. What I'm going to do now is say File, New File, and I will say Save As, and inside of my main package, and I'm going to create some main script.py, save that, and then what I'll also do is say File, New File, and let's put another .py script inside of my sub package. So we will say file, save as, and inside of this sub package, along with that other init file, we're going to create the following. We will say my subscript.py. So now I have this outside module, some main script inside of that main package folder, this subscript inside of that sub package folder, and then my main program. So what we can do is we can start playing around with this all the way from my program. So what I'm going to do is inside of my subscript, we'll say def, then say sub report, and have that print out, hey, I'm a function inside my subscript. Control S to save that. We're going to do a very similar thing here in some main script, and we'll say def. We'll call this report main. And this will print out, hey, I am in some main script in main package. Save that as well. Okay, so let's take a look at the directory right now. We'll say open file just so we can explore this. So at my desktop right now, I have this mymodule.py. We won't really be playing with that anymore, but instead I have this myprogram.py. And we can think of myprogram.py as the main.py script I want to run. And I want to organize my files into packages. So right now we've explored how to actually create a single module, which is just a .py script. And you can imagine we'd be importing from various modules, so various .py scripts, but at a certain point, it's going to be too much and we want to organize them into folders. So the way you would do that is you would have packages, which are just directories that have this init.py, so __init__.py, and that tells Python, hey, this actual directory, it has a bunch of modules in it, so you can call them using a certain syntax, which we're about to show you. So here we have some main script. You can imagine I could have many more .py scripts or many more .modules inside of this main package, and we can keep going with sub packages as long as they have this init.py, and here I can see my subscript. So I'm going to cancel this, and what I'm going to do is inside my program.py, I've already know how to import from a module, but now let's realize how to import from a package. To import from a package, what I can say is from my main package, I can either import the actual module itself. So remember the module in my main package, it was called some main script. So we'll say some main script. And if I wanted to import from a sub package, what I would do is say from my main package dot sub package, and then I can import some module from there. So in this case, it was called my subscript. So this is now how you can organize not just into a single directory, but you can actually organize into subdirectories as well. And this is the syntax for that. You say dot, the name of that sub package, import, and then import the modules. And if you want, you can go even further and actually import only specific functions. So we'll show you how to do that in just a second, but let's actually call the functions from some main script. So from some main script right here, we want to call the function that's inside that script. So if we click back here, we realize that that one is just called report main. So coming back, we'll say some main script, report main, close parentheses. So we're actually executing the function report main, which is under some main script module, which is under my main package. Then we also want to, if we look at my subscript, that has the sub report. So let's run that as well. We'll say my subscript, call sub report, open close parentheses. So let's save that, and then let's run my program.py at the command line so we can see what happens. All right, so now here back on my desktop at the command line, I will say Python, call my program.py, and I hit enter, and now I see, hey, I am some main script in main package, and then, hey, I'm a function inside my subscript. And that's it. Now you've successfully not only created a module in the first part of this lecture, but you've also created packages and sub-packages. And in general, the idea here is just how do you organize various Py scripts. As you begin to grow better and better in Python, you're going to write more and more Python code. So at the beginning, you'll create a couple of modules. They'll all be in the same folder, no big deal. Then, as it starts getting more and more unwieldy to have it all in the same folder, all you need to do is create directories that have that special underscore underscore init underscore underscore .py file. That just tells Python, hey, this is now a package, and it allows you to run what we see here, this my main package, my main.sub package. Okay, that's the basic idea of packages and modules. If you have any questions, feel free to post to the Q&A forums, and we'll be happy to help you out there. I'll see you at the next lecture. To finish off this section of the course, I want to discuss these two ideas of name and then the string main. So an often confusing part of Python is when you start looking at larger .py scripts that you haven't written yourself, you often see at the very bottom this mysterious line of code that says if underscore underscore name underscore underscore is equal to the string underscore underscore main underscore underscore colon, and then there's a block of code to be executed. So sometimes the whole idea behind that line of code is that when you're importing from a module, you would actually like to know whether a module's function is being used as an import or if you're using the original .py file of that module. So what we're going to do is explore all of this a little bit more, but make sure to check the full explanatory text file that has a written explanation of everything we're going to cover here. What we're going to do basically is just create two simple .py scripts and try to show you the idea behind that if name is equal to main block of code that is usually at the end of larger .py script files. Let's get started. Okay, let's begin by actually creating two new files. We'll create them at my desktop. I will say for this first file, save as, and I'm going to save this as 1.py. So this one is 1.py. Then I'll create a new file, and I'm going to save this one as 2.py. 2.py, again at my desktop, so we'll label this one 2.py. So make sure you have those saved. So let's think about what actually happens when you call a Python script at your command line. You go to your command line and you type Python space the name of your script .py. So what's actually happening when you call Python myscript.py, all of the code that's at indentation level 0, essentially something like this, is going to get run. So that means any code that's at indentation level 0 is going to get run, and that would mean that your functions, which are automatically usually going to be defined at indentation level 0, and your classes, also at indentation level 0, are all going to be defined. So unlike other languages, in Python, there's no main function that you call somewhere at the top of your script that gets run automatically. Instead, what happens is, just implicitly, all the code at this indentation level 0 gets run when you call the script file. And you probably have an intuition of that by now, since we've been working through that strategy the entire first half of the course. Now, in Python, there is actually a built-in variable called name. So just like there's built-in functions, this is a built-in variable. And it's quite obvious that it's built in because we have two sets of double underscores in the beginning and in the back of it. So that would allow you to have to really try to overwrite it by accident. So what happens is this variable name gets assigned a string depending on how you're running the actual script. And if you run the script directly, so if I went to the command line and I wrote out Python space 1.py, what Python is going to do, it's going to assign this built-in variable called name to be equal to underscore underscore main. So Python does this in the background. Well, it really does this. It assigns this string to the name variable when you run it directly. And that allows you to have an if block to check if they're equal to each other. So often what you do is something like this. You say if name is equal to main, and then you can do something because you know that this particular .py file is being run directly. And if you ever run something directly of Python, you know this case happens to be true. So what happens is often people will just, at the very bottom of their code, they'll say if name is equal to main, and then they say kind of run a bunch of functions that they defined here. So at top, they do a bunch of function definitions. So function number 1, function number 2, so on and so on. So you can imagine hundreds of lines of function definitions or classes. And then all the way at the bottom, they actually organize their code on what they actually want to execute. And they know that they want to execute it because they say, if this built-in variable called name happens to be equal to the string main, then I know I'm running this .py file directly. So we're going to explore this whole idea a little further. And to do that, we're going to do the following. In 1.py, so let's go back here. This is 1.py. I will write out the following code. I will say def, create a function, and this function is going to be very simple. It will say func in 1.py. So when you call that function, it says func in 1.py. It's just printing that out. And then what I'm also going to do here is at an indentation level of 0, so outside of this function, I will say top level in 1.py. So now I have a function definition as well as a global print statement top level in 1.py. Then at the bottom of this, I will say if, and you'll notice that Sublime Text Editor will actually autocomplete this for you. If name is equal to main, I'm going to delete this. So I have an if block of code here. So if name is equal to main, then I know I'm running this directly. So I will say 1.py is being run directly. And then I'm actually going to line up an else block with this if statement. You don't see this that often. You usually just see if and then you execute all your code. But just to make it clear how this variable is working, we'll also add in an else there. We'll say else print 1.py has been imported. So I'm going to save that, and let's take a look at what happens. I define this function, I print out this statement whenever you call 1.py, and then depending if 1.py is the main script, meaning I'm calling 1.py directly at the command line, I will print this out. Else, that means the variable name was not set to main, and I will print this out. 1.py has been imported. So now let's work with our second file, 2.py. What we'll do here is say import 1, and I will print out at the very top level. Let's print out something like top level in 2.py. And since I just imported 1, let's execute the function that's from 1. We'll say 1.func. And here we're going to have an if statement. We'll autocomplete this. If name is equal to main, I will print 2.py is being run directly. Else print 2.py has been imported. So let's save the changes in both of these and then open up our command line. All right, so the first thing we're going to do at our command line is actually run 1.py directly. So we run this and we notice what happens. We get that print statement, top level in 1.py, and then we see from that if name is equal to main, 1.py is being run directly. So we can see here that that built-in variable underscore underscore name underscore underscore has been assigned that main string. So Python then knows, and the entire script can know, that 1.py has been called directly. But now let's check out Python 2.py. So now when I run this, notice what happens. I get back top level in 1.py, but now 1.py, its built-in variable of name has not been set to main because it's been imported. So now we get back 1.py has been imported. And then I get top level in 2.py, func in 1.py, and then 2.py is being run directly. So that built-in variable actually allows you to see whether something is being imported or run directly. So that's the idea and concept behind the variable name, and checking if it's equal to main. Typically, however, what you see is people, they don't really do it the way we've done here where they check is something being run directly or not. Instead, if we come back to Sublime Text Editor, what they do is instead of having an else statement here, since they just say if name is equal to main, this is the same thing as saying run the script, right? Because we already know that if this happens to be the case, then someone is running 1.py script directly. So what they do is they define a bunch of functions up here or define their classes. So here's another function, pass. You write some other function, function2, save, and then down here at the bottom, what you end up doing is you just call your functions. So you'll say, okay, execute function2, then execute function1, and then maybe you have a little bit of logic here. But the main idea is that this is more for code organization. You have all your functions and classes defined up here, And then your logic, where you actually execute things, are defined here at the bottom. And this is a really common structure you'll see for larger .py scripts, especially when you begin to use modules and packages. All right, that's the basics of this line, if name is equal to main. Definitely check out the explanation.txt file that goes along with this lecture, and if you have any questions, feel free to post to the Q&A forums. I'll see you at the next lecture. Welcome back. In this lecture, we're going to be discussing errors and exception handling. Errors are bound to happen in your code. Nobody's perfect, and errors are definitely going to arise, especially when someone else ends up using your code in an unexpected way. We can use error handling in an attempt to plan for possible errors that may arise in our code in the future. For example, maybe in some part of your code you try to open up a file. So later on, someone else is using your code, and the user may try to actually write to the file when it was actually only opened with the mode R for reading. Currently, if there's any sort of error inside our programs, the entire script's going to stop and we get back some sort of error statement. We can actually use error handling to let the script continue with the other code and report the error. So even if there's an error, the code will report the error and continue on. Now there's 3 keywords for this entire process of exception handling, and it's the try, except, and finally keywords. And these are all going to have a block of code associated with them. So under the try block of code, that's the block of code that's going to be attempted, and this may or may not lead to an error. So once you try the actual try block of code, if there is an error, you have the except block. And this is a block of code that will execute in case there's any error inside of that try block. Then you have a finally block of code, which is a final block of code which is always executed whether or not there's an exception or error occurring. Let's jump to the notebook and see some examples of how to use these blocks. Okay, let's start off by actually viewing an example of some error that may occur. Let's imagine that we have a very simple function, some add function, takes in n1, n2, and then what it does, it just prints out the sum of them, n1 plus n2. You may be thinking, no problems here, I'm just going to say add 10 and 20, and you get back 30. But let's imagine you have the following situation. You have some variable, number 1, and you set that equal to 10. Then you have a bunch of code, and later on, to get the second number, you ask for it as an input. And let's say number 2 is equal to the input of please provide a number. So it asks us, please provide a number, we say 20, and then what we end up doing is we say, well, let me call that add function again on number 1 and number 2. Hopefully you realize that this is already going to give you an error, because recall that when you call the input function, 20 here is actually a string. So when I run this, it says, hey, you have a type error. So notice here that there's an actual specific exception that Python's trying to tell you about, type error. And it says unsupported operation, type S, for plus, integer, and string. It's basically telling you, hey, I can't add an integer and a string together. I can add 2 integers together, or I can concatenate 2 strings together, but I can't work with both these data types. And this is an example of the type of error you may get while running your code. And unfortunately, let's say I wanted to have a print statement. So let's say something happened, and I run this print statement is never actually going to occur. What's going to happen is I get an error, and that's the end of my script. Doesn't matter if I have hundreds of lines past this block of code, I will still get this type error, and nothing else after it is going to get executed. The idea behind the try and except and finally statements is that even if an error happens, we're going to try to do that block of code, and even if there's an error, we can continue with some more code. So how will we actually do this? Well, we have the try keyword, colon, and then we have the block of code. So this is the code that you want to try. So you want to attempt this code. However, it may have an error. So here I'm going to say result is equal to 10 plus 10. Whoops. There we go. So we know this is not going to actually induce an error. And then what I'm going to do here is I'm going to have my except block of code. So my except block of code is what I want to have happen if there is an error. And this is really common when you're building out larger libraries that other people are going to use. You can have except blocks, so you can print out a more specific message to the user. So maybe you can say, hey, it looks like you aren't adding correctly. So I'm going to run this, and notice we actually don't induce an error. Instead, I can call result here with no problem as 20, which makes sense because 10 plus 10 has no problems. Let's now actually create that error. I'm going to try to add the integer 10 to the string 10 here. Now when I run this, it says, hey, it looks like you aren't adding correctly. Now notice what happened here. The rest of the block of code was still able to execute with the except statement. My whole program wasn't shut down just because I had some sort of error like before. Instead, I tried this block of code and then I said except. And in general here, I can say except if there's any type of error, do this code right here. Now let's imagine that I want a block of code to execute if there is no exception. I could do something like this. I can say else print result, and above that I can say print add went well. So right now when I run this, it just says, hey, it looks like you aren't coding correctly. So this is known as a try except else statement. And what we have here is the block of code we're going to try, and then we have two options. If there is an error in that try block, we run the except code. Else, if there is no error there, we run this else code. So let's fix this and have it not produce an error anymore. We run this. We try this block of code. Since it was successful, we don't execute this except block of code. Instead, we jump straight to else and we say add went well, and we have 20. Okay, so let's try except else, and we can now actually use the finally keyword to have a block of code always executing, regardless if there's an error. So to show this, I'm going to build off of an example where we actually try to write some files. So let's explore this concept of try, except, and finally by working on a new example. And in this example, we're going to try to open up a file. So we'll have some test file, and we're going to start by opening it in W mode. That's write mode, which allows us to either open the file and write to it, or create the file if it doesn't already exist. And then I will say f.write, and I'm going to write a test line to this file. And then I will say except, and here I can either say except colon, and that's going to accept for any errors, but there's actually many types of errors I can specifically accept for. For example, I can try to only accept for this type error. So what happens is, notice above we had this specific type error. What I could do is say, hey, only if there's a type error, print out there was a type error. Then I could try another error that's actually associated with opening and writing files. And if you go to the documentation, you can come to errors and exceptions, and this explains syntax errors and exceptions in general, but you'll notice there's a link here to built-in exceptions, which jumps you to section 5 here of the documentation, and this is actually a list of all the different types of exceptions and errors that may happen. So if you keep calling down, there's an assertion error, there's end of file error, import errors, index errors. Some of these you may have seen before, a lot of them we haven't seen. There's OS errors, recursion errors, overflows, all different kinds of errors that you can specifically try to catch. So in our case, the error that's going to occur when you're opening and writing to files that you don't have permissions to is an OS error. And we're going to print, hey, you have an OS error. You can also say IO error, depending on what version of Python you have. And then we're going to add in a finally block. And this finally block is always going to execute no matter what. So say I always run. I'm going to run this right now. And right now we just get back I always run. So what's actually happening here? Well, we open up the test file, we call write on it. So that all works, meaning I don't have this except block running, and I don't have this except block running. So then I just say, finally, I print, I always run. Now let's actually induce an error by opening it with R. So that's read-only permission. So we should get an error on this line when we try to write to the file. Now we shouldn't get a type error because that's not actually the error we're getting. Instead, we should get an OS error because that's the error that's related to trying to write to a file that you only have read permissions for. So if I run this, I get back, hey, you have an OS error. And unlike last time where we had this except else where only one of these blocks was going to run, with the finally statement, the except block will run and then the finally block will run. And this is how you can line up a bunch of excepts to have specific things print for specific errors. What you could do is, let's say you have type error here and you didn't want to memorize all the other types. If you just say except at the end of this, this is going to be all other exceptions. So all other exceptions. And I rerun this again and it says all other exceptions because it didn't detect the type error or any other errors that we defined. So if you just say except colon, you'll print out that error. Okay, so keep in mind as you're beginning in Python, you probably won't memorize all the error types, and most likely your blocks of code are just going to look like this: try, except, and finally. So just to reiterate, the try block of code is the block of code you're going to try to attempt. The except block of code is going to occur when there is an error in your try statement, and then you have the option of putting a finally block here that will always run whether or not there's an error. Or you can have an else block of code that's only going to execute when there's not an error. Okay, so let's focus on this one more time here. Right now, there is going to be no error because I will say W there. If I run this, I get back I always run. So there's no error, finally block still runs. We induce an error. We say all other exceptions because I'm just saying in generally except here. It does whatever this block of code says. Finally, it does this block of code, so this finally block, regardless if there's an error, it's always going to run. So let's finish off our discussion here by showing you how to use the try except finally blocks inside of a function that tries to get a specific type of input from a user. So what we're going to do here is the following. We'll say def ask for int. So what this function does is it's going to attempt to ask the user for an integer. So we'll say the following. Try to result is equal to integer of the input. Please provide number. And then if we get an error here, I'm going to say except, and I'm going to print out, whoops, that is not a number. And then I'll say finally print end of try except finally. So I run this and we're going to iterate on this function in just a little bit, but I'm going to call this function right now, do shift enter. It asks me to please provide a number. Let's give it one, 20, and I just get end of try except finally. It makes sense that whoops, that is not a number didn't print, because we were successfully able to cast or transform 20 into an integer. But what happens if I run this cell again, and now I provide a word? Now I know I definitely can't transform the string's word into an integer. So when I run this, it says, whoops, that is not a number, and we get an end of try except finally. So let's see how we can now use a while loop to continually be doing this try block of code, and then except if there's an error there. Okay, so let's see if we can adjust this function so that instead of just ending after you provide the wrong word, we're going to put it inside of a while loop that keeps going over and over again until you actually have a block of code with no exception. So what I'm going to do is say while true, and you should always be careful when doing while true because it basically means you need to use a break statement somewhere to break out of this while loop. I'm going to indent all of this, so highlight it all, hit tab here, and I'll say while true, get this result as the input. Then I say except, whoops, that is not a number, and then I'm going to say continue, just to make this a little more readable as far as the logic of what's happening. Now let's say there is not a error. Then I'm going to say else, so you can actually combine else with finally here. So we're going to try this block of code. If there's an error, I'm going to say, whoops, that's not a number, continue on. Else, meaning there is no exception. That means the user did provide an integer, so I will say, yes, thank you. And now I need to break out of this while loop. So I will say here, break, which remember the break statement goes up to its enclosing loop, either while loop or for loop, and then ends it. So it will end this while true loop. Then finally, we'll say end of try except finally. Okay, so we just put these 4 blocks of code inside our while true, and we're going to break once we say yes, thank you, and we'll have a finally statement that says print end of try except finally. And we can just make it very clear that print I will always run at the end. So regardless if there's an error or not, this finally block of code is always going to run. So we're going to run this, ask for an integer. Let's provide it a correct integer. We'll say 20. Hit enter. It says, yes, thank you, end of try except finally, I will always run at the end. Let's provide it a string. We'll say q. Hit enter, and it says, whoops, that is not a number. End of try except finally, I will always run at the end. Except we have while true here, and this break hasn't actually executed yet. So we have another chance to provide it a number. We'll say q, it says whoops again, and you can keep providing it over and over the wrong things, and it's going to keep asking you for input until you finally provide something that can actually be cast as an integer. You say 90, and it says yes, thank you, end of try except finally, I will always run at the end. So note what's happening here. We're saying while true, try this block of code. If there's an exception, do something and then continue. Else, meaning there is no exception, you can print some sort of statement and then break. And typically, you're only going to want to break out of this while true when there is no exception. Then finally, if for some reason you wanted something to continue, so a good thing here could be like, I'm going to ask you again, new line. So that's more a realistic example of why you would say finally. So if I run this again, it'll say, please provide a number. We give it the wrong answer. It says, whoops, that is not a number. I'm going to ask you again. Please provide number. And then you can provide it the correct number, and it says, yes, thank you. Now, unfortunately, it's going to say, I'm going to ask you again. So that's why a lot of times people don't like to mix up else and finally statements, but there's the option for you in case you want it. What you could do instead is just get rid of that finally statement and run your code like this, and you'll say, please provide number, q, whoops, that is not a number, and you can keep doing this over and over again until you actually provide the number and it says, yes, thank you. It's up to you whether you want to mix else and finally blocks, but you can if you want to. All right, that's the basics of try except else. Coming up next, we're going to give you an assignment to test your new skills on this. We'll see you there. Welcome back, everyone. Now that we understand how to work with errors and exceptions handling, let's get some practice with a quick homework set of 3 problems. Let's go over the notebook so you can attempt it yourself, and in the very next lecture, we'll go over the solutions. Okay, so you can find this notebook under Errors and Exception Handling. It's the second notebook, Errors and Exceptions Homework. The very next notebook is the solutions. So there's 3 problems in here. The first one is to handle the exception thrown by the code below by using try and except blocks. So notice here we're saying for I in this list of strings, I'm trying to square the actual strings. That doesn't really make sense. So try to use a try and except block to handle this somehow. That's a pretty open statement, so you can just print something like an error occurred and then maybe have something else happen. Basically, just don't have this type error pop up. Problem 2 is to handle the exception thrown by the code below by using try and except blocks as well, and then use a finally block to print all done. So right now we have a 0 division error, so we're trying to say 5 divided by 0. Go ahead and catch this exception and then have a finally block execute. Then problem 3 is kind of similar to what we discussed towards the end of the previous lecture, and it's to write a function that asks for an integer and prints the square of it. I want you to use a while loop with a try except else block to account for incorrect inputs. Okay, best of luck, and we're going to go over the solutions in the very next lecture. Welcome back, everyone. In this lecture, we're going to go now over the solutions for the errors and exceptions homework problems. Let's open up Jupyter Notebook and get started. Okay, taking a look at the first problem, it was to handle the exception thrown by the code here below. So let's copy this and put it in a new cell. If I just run this by itself, we get that type error because we're trying to square a string, which doesn't really make sense. So what we need to do is put this whole block of code inside of a try block. And this is where indentation is really going to matter, because now we need to indent everything. in order for alignment. So we have this try block right here, and then we can make an except call. And it's up to you whether you want to say except and catch that specific type error, and then print out type error or whatever you want. So if I run this, it says type error, watch out. Or if you don't want to catch this specific error, just any error, you don't actually need to say that. You can just say except, and you get the same thing. In this case, it wouldn't be a type error. We could just say something like general error, watch out. Main idea being that you need to put that piece of code inside that try block, have an except line up with it, and then say something. Let's move on to problem 2. This was to handle the exception thrown by the code below using try and except blocks. Then finally, block to print all done. I'm going to copy this, put it back here. And if I just run this, let's confirm that we get an error. Looks like we're getting a 0 division error. So let's put this all inside of a try block. We will say try and indent all of this into the try block. You could also just highlight it all and then hit tab. Then I'm going to say except. And again, I can either say except 0 division error or just except by itself. We're going to print out error. And then finally, we will print out all done. Hopefully this was pretty straightforward. So we say error, all done. And then the last one, probably the most complicated of them, was to write a function that asks for an integer and prints out the square of it. Use a while loop with a try except else block to account for the incorrect inputs. So we're going to copy this. We did something very similar in the lecture. So what are we going to do here is say while true. And it's up to you if you want to say while true or while some condition. So I'm going to say while true, try to say n is equal to the integer input of enter a number. Now, if we have some sort of exception, and we're going to assume that the exception occurs when you try to transform that into an integer, we'll print out, please try again. And then let's print out a new line, and we'll say continue. Now, else, that means there's no exception. What we can do is say break. Optionally, you can have the finally in there, but remember the finally is going to occur every time. So let's run this and make sure this works. So we're going to say ask, shift enter to run that, enter a number. Let's say we enter 10, and it looks like we forgot to actually print out the squared, which was what was asking us. If we come back here, I want to say thank you, your number squared is, so let's do that. And this is going to be outside of that while statement. So once this entire while loop is done running, we should have n ready to go. So we're going to print n to the power of 2. And we can say above that, print your number squared is. There we go. Okay, so now let's try this again so we actually get the results. We'll ask this again, enter a number. We'll say 10, enter, number squared is 100. So that's working. Let's now try to do something wrong. So we'll say A, and it says please try again. We'll say WE, please try again. Let's enter 2 now, and the number squared is 4. Okay, so that's how you can use a while true. So notice that while true is dependent on this break keyword. What you could do instead is say while something like waiting, and we can set waiting to be equal to true. So this is saying like we're waiting for a correct response. You can call this variable whatever you want. So I'm waiting for a correct response. I'm going to try this. I'm going to have the exception. Else, if there's no exception, then I can set waiting equal to false. I'm no longer waiting for the correct response. So that's the same thing, except we're not using a break statement. So we can try this again, make sure that tactic also works. Let's enter the wrong thing. Please try again, enter the right thing, and it works for. Okay, so that's it for errors and exception handling. If you have any questions, feel free to post to the Q&A forums. I'll see you at the next lecture. Welcome back, everyone. Now that we understand how to handle errors and exceptions in Python with the try, except, and finally blocks of code, let's move on to discussing unit testing. As you begin to expand to larger multi-file projects, or you begin to work with a team that's bigger than just yourself, it becomes really important to have tests in place. This way, as you or your teammates make changes or update your code, you can run your test files to make sure previous code still runs as expected. There are several testing tools, and we're going to focus on two. There's other ones mentioned in the notebook that goes along with this lecture, but we're going to focus on Pylint, and this is a library that in general looks at your code and reports back possible issues. Maybe you have styling issues, or maybe you have some invalid code, and it will report back issues with your code. Then we have the unit test library. This is a built-in library in Python that's going to allow you to test your own programs and then check if you're getting the desired outputs. We're going to begin by showing you how to use Pylint to check your code for possible errors in styling. And if you're wondering what I mean by styling, Python has a set of style convention rules known as PEP8, and we'll show you those in the documentation. And then afterwards, we're going to explore how to test our code with the built-in unit test library. For this lecture, we're going to be creating .py scripts in Sublime because that's a more realistic example of how you'll actually be using these programs. You can still use the associated notebook for code. It has a bunch of write file magic Jupyter commands to create the .py scripts. So if you're really intent on sticking with Jupyter, the Jupyter notebook does work for this lecture, but in the actual filming of this, we're going to use the text editor because it's a little more realistic. Okay, let's get started. Okay, the first thing we need to do is install the Pylint library. So let's go ahead and do that at our command line. So if you're at your command line or your terminal, if you're on Mac OS or Linux, all you need to do is straight into your command line, don't call Python before this, is just say pip install Pylint. Hit enter, so that's Pylint. Right now, I already have it ready to go because it came with my distribution of Anaconda. That may be the same case for you, but make sure you run this line just to check that you have it already. Once you have that ready to go, let's go back to our text editor. Alright, so here I am at the text editor, and I'm going to create a very simple .py file. So let me say File, Save, and I'm going to save this to my desktop, and I will save this as simple1.py, which is a very simple file. You can save it wherever you want, as long as you're able to call it at the command line. If you're unfamiliar with how to actually run scripts like this, make sure you go back and visit the lecture at the beginning of the course called Running Python Code. Okay, so I will say a is equal to 1, and notice I have syntax highlighting. That means it's registered as a .py file. Then I will say b is equal to 2. Notice my lower cases here. Then I will say print a, and then I will say print, and I'm going to make a mistake here on purpose. I'm going to say print capital B. Even Sublime Text is telling me, hey, I think you mean lowercase, but we're going to ignore that for now. So it's just a very simple script, but there's definitely a mistake in it right here. So as you can imagine, with 4 lines, it's pretty easy to catch this mistake, but if you have a script of hundreds of lines, it's going to be much harder. So do Control S or Command S to save this, and once you have it saved, come to your command line. And then what we're going to do here is say Pylint. So notice I'm not saying Python. I will say Pylint, and then say simple1.py. Remember that you have to be at the same location as your .py script, and you can view the command line lecture to get an idea of how to move around at your command line. But let's hit enter here and see what happens. Okay, so we actually get back a bit of a report here. And what Pylint does is it issues what is essentially an automated report grading your code. So if we scroll all the way back up here, it says no config file found using default configuration, so you can set more advanced configurations. And we have final new line missing, so we have some issues, and these are styling issues. We have an invalid constant name, but most importantly, notice here, this is an actual error, so it has an E here, and these are the ones you really want to watch out for, an undefined variable B. So later on, it gives you statistics as far as whether you're using functions, method, classes. So if for some reason you want to figure out, well, how many classes do I have? How many functions do I have in this code? And are they documented? Do they have a stylized name that's inappropriate? For example, maybe you accidentally capitalized a function. So this would be giving you statistics on that. Then it gives us raw metrics, such as how much code are there, how many doc strings are there, comments, how much is empty. So if you're working with other people and you demand, hey, every other line should have a comment on it, you could use this to quickly check. Now, whether or not you need that many comments is up to you, but hopefully you can see in more of a management position how these sort of reports would be really helpful, either to give to your manager or to receive as a manager. Then we have duplication, so how many lines have been duplicated. Right now we have 0 because it's such a simple file. Then we see messages by category, so if there's errors, warnings, so here we're actually getting an error. So notice it ran the code and it got an error, and then we have some more information about messages. And these are what kind of messages actually rise up when you run that Pylint report. And here we're getting a bunch of messages. We have undefined variables, there's missing doc strings because it's just a simple file with a huge mistake in it. So global evaluation, at the very end, it's going to evaluate your code, and here we're getting a horrible evaluation, which is negative 12.5 out of 10. So perfect score is 10 out of 10, and here we're doing absolutely horribly with negative 12.5. So Pylint, it's listing some styling issues. It would like to see an extra new line at the end. Modules and function definitions should have descriptive doc strings. Single characters are also a poor choice for variable names, so it's kind of complaining about that too. And most importantly, out of all of this, it found that error in the program. So let's try to clean this all up and see what kind of score we can get. And I should note here, it's pretty difficult to try to aim for a perfect 10 out of 10. So don't be stressed if you're not getting a 10 out of 10 on your own code. Sometimes to get something 10 out of 10, it has to be very machine readable instead of human readable. And you always want to balance that if someone else views your code, they're going to be able to read it easily. However, we can definitely make some improvements here. So let's see what we can. Okay, so back at the script, let's see if we can improve this whole thing. Often when you're dealing with a .py script, you're going to want to have a multi-line comment at the top just so other developers can come in and understand what's going on. So here we're just going to say a very simple script. So that should help us score some points with Pylint. And then we're actually going to create a function definition. So we'll say myfunc, won't take any parameters. And again, we should give our functions a doc string. I'm going to zoom out just a little bit here so we can see the whole picture. And here we're going to say a simple function. And then let's actually create two new variable names. First is equal to 1 and second is equal to 2, because usually you don't want to use just a single letter as a variable name. And then we'll print out first. And then what we're going to do is we're going to print out second here. And at the end of this, we're going to actually execute the my function. So we'll say myfunc, open close parentheses, execute at the bottom. So notice here the indentation. I'm going to save this, and let's run this again in Pylint and see if we were able to improve our score. Again, most likely we won't get a 10 out of 10, but we should see a big jump from negative 12. All right, I'm back here at my desktop. First, let's just make sure that our script actually runs. We'll call simple, or Python, simple1.py. You should be able to tab autocomplete that. And we get back 1 and 2. Looks like it's running. Let's now check the score. We'll say Pylint simple1.py, hit enter. And now we get back 0 out of 10. So it looks like we still have some issues, but we're no longer getting negative 12.5 out of 10. All right, now you may be looking at this and saying that it looks like a lot of our problems are with mixed indentation. And if you scroll up here, you'll realize that it's telling you about all these warnings. It's found indentation with tabs instead of spaces. Due to styling issues, especially with different text editors, so let's say your colleague opens this up in PyCharm and you're opening it up in Sublime, someone else is opening it up in Atom, you typically, when you're working for other people, want to use spaces instead of tabs. Now again, this is very much just a styling choice. The code will still run fine. As we just saw, they had no problem issuing that code, but Pylint is going to complain about this issue. And you can check the documentation and say, don't worry about this particular warning. Usually you do want to have it warn about mixed indentation, but you don't want to have it warn about pure tabs or pure spaces. So in order to fix this issue, you can go back to your script. Let's do that now. So here I am at my function, and you'll notice that when I was defining my function, all I did was hit enter, and then that basically auto-tabbed for me. So if I hit delete or backspace right now, it will go back one tab. So to fix that, what we can do is make sure everything is defined as spaces. So delete this right here, and then do 1, 2, 3, 4 spaces. And if we do that for every line, I've actually already done that for you. I've actually already done that myself on this script. We've done that for you in the Jupyter Notebook as well. But now you should be able to improve on that. So I'm going to save this. And if you ever have a doubt, are these tabs or spaces, in Sublime Text Editor, you should be able to highlight. And here, it probably won't show up on your screencast, but I can see 4 very faint dots indicating each space. And if you just have a tab, you won't see that. So you'll have to see that on your own screen. But again, it's just highlighting this, and you can see the spaces. And if you have just enter, you'll end up seeing a tab here, just one straight line. So Pylint will complain when you mix those together. So let's save this and go back to our command line. And now I'm going to rerun Pylint on my simple1.py script now that it only has white spaces. I'll hit enter. And it looks like now we're getting much better. We're getting 8.33 over our previous run. And you may got 6.67 after fixing that. I've run this a few times trying to deal with that white space issue. And this is most likely probably about as best as we're going to get without having to put in a bunch of extra comments and code. Okay, that's really all we need to know about Pylint for our use cases. And in general, when you're just coding by yourself, you won't be using something like this that often. This is really more for when you're working with other people or you're working with really large programs and you have kind of strict methods for yourself to make sure everything is up to some sort of style convention. Again, it's not really useful for just a rating to come back to a single user because you just saw the entire bit of code. Okay. So that's Pylint. Coming up next, we're going to learn about unit test, which allows you to write your own test programs. Notice here that we're basically running a bunch of tests. It'd be nice if we could write our own. We'll see you at the next lecture. Welcome back, everyone. In this lecture, we're actually going to go over the unit test library. So unit test allows you to write your own test program, and the goal is to send a specific set of data to your program, analyze the returned results, and then see if it actually gives you the expected result. So let's actually create two scripts here. One is going to be a simple script that capitalizes text, and then the other script is going to be the actual test script for this. And you're going to need to review object-oriented programming to understand how to use unit tests because you do build out a test class. Let's get started. Okay, here I am at Sublime Text Editor. I'm going to create two scripts. We'll say new file, save as, and on my desktop, I will save the first one as cap.py. So this is the script that's actually going to capitalize given text. And then the next script will say file, new file, file, save as, and I'm going to save this. And technically you can call your test script whatever you want, but we will call this one test underscore cap.py. Save that, and those are both saved right now in the same location. So our cap.py file will be very simple. It'll just have a single function inside of it. And this function takes in some text. And then what it does, it's going to return text dot, and we're going to capitalize the text. So if you don't recall, capitalize method on a string just capitalizes the first single letter. It doesn't actually uppercase everything. So you can check that yourself quickly at the command line, but that's what the capitalize method does. We expect text to be some sort of string. So basically here, we're going to input a string, output decapitalize string. And by capitalize, we just mean capitalize that first letter. I'm going to save this. So cancel, save that, go to test underscore cap, and this is where we actually use the unit test. So when writing test functions, it's best to go from simple to complex, as each function is going to be run in order. So you usually want to test simple things, and then later on test the more complicated things. The first thing you need to do is import unit test, and then you're going to need to import any of the files we want. And because these files are both saved at the desktop location, I'm going to say import cap. So that actually imports my other .py script, this cap.py. So I've imported unit test. That's a built-in function. And whoops, let's make sure I spelled that right. It has two T's, so watch out for that. It's unit test, two words in order. Import cap, that's the cap file we just created. And then we're going to create a class. And we'll call this class test cap. And we're going to inherit the test case class that comes with unit test. So we say unit test dot test case. So if this syntax is strange to you, you can review the inheritance lectures in object-oriented programming. But here we're just going to have a list of methods, and these methods are basically going to be run when we test this actual script. So we'll say def test one word self, and this is just going to be set text equal to the simple word Python, and the result is going to be, we'll say cap, and we'll call the cap text function. So what I'm doing here is I'm importing cap, and then from cap.py, I'm importing this cap text function. So I'm saying cap.cap text function, and I will pass in the text, so that's lowercase Python, and I would expect my result to be equal to the following. We say self dot, and we call assert equal. We pass in result, and then we pass in Python with a capital P. And this is the general structure of a test. And when you look at it, it's actually really quite simple. All you do is you create your class to be called at the end. You inherit from unittest.testCase, and then you have a function to be called. In this case, we call it test1, and usually you number them like test1, test2, or you maybe have names that refer to what they're actually doing. So here we could have test one word, and then the next one could be testing multiple words. So here we have text is equal to Python, and then you call whatever functions you want to test off your script. So that way, if someone comes in and they start editing cap.py, and you want to make sure that this function always returns the same thing, you now have this test that will assert that. So you get the result of something passed into that function, and then you say self.assert equal, and you're saying, I need that when this lowercase Python gets passed into the cap text function, that it always returns back the capitalized P version of Python. And then we can add in another test. So we can say DEF, and we can call this test something different. You can either number them, or you can define them as far as what they're testing. So maybe we want to test multiple words. We'll say self, and then we'll add in some text here, and set that equal to, let's have it be 2 words, Monty Python. And it's basically the same thing here. We say result. So copy and paste that. So I want my result to be passing in Monty Python to text. And then I will say self.assert equal. Let's copy that line as well. Onto the new line, except in this case, when you call capitalize on this string, what it should do is capitalize the first letter of each of these words. So I should expect to see Monty Python. And at the end of all this, we can say if, and you underscore, name is equal to main. We will call the main function here, unittest.main. So save this, and let's actually now run our test cap. All right, so what we're going to do here is actually run our test code. We'll say Python test underscore cap, and you can auto tab complete that. We'll hit enter, and right now it looks like we're actually getting a failure. So you get this failure report, which is kind of nice. It says fail, test multiple words. It says Monty Python. Notice here how the P is being lowercase, does not equal Monty Python. So now we're scratching our heads thinking, well, what's the issue? Is it my test or is it my actual file? And that actually depends on the situation, but typically you're going to say, hey, I need to adjust my main script so that I make sure my testing works. And a lot of times in larger companies, you'll have someone in the QA department, quality assurance, actually writing these tests to make sure that your scripts work as they expect them to. And if we think about this, the actual issue is, as we previously mentioned, capitalize, all it does is it capitalizes the very first letter of a string. That means that if we take a look at Monty Python, and you may have noticed it as I was writing, that this is actually not going to happen when we call capitalize. And there's actually a different method for this. If I want both these letters to be capitalized, then what I need to do is instead of calling capitalize, there's actually a method called title. And that will then capitalize every single word instead of just the first letter of the string. So now let's save those changes using title and see if we pass this test. So we'll come back to the command line. And now what I'm going to do is run the same thing as I did before, Python test underscore cap. We hit enter and it says ran 2 tests and everything okay. That means you passed all your tests. Okay, that's basically all you need to know about unit testing. So let's go back and do a very quick overview, but the actual idea is very simple. So you have your scripts, and this could be lots of scripts, it could be a single script, and you call functions or classes, whatever you want. And then inside of your testing script, what you're going to have is you're going to import unit test, import any of the scripts you've been working on, create a class for testing. You're going to inherit from unit test test case, and then you're going to have methods to test for any situations you can think of. So you'll set whatever variables you need, and then at the end of the day, somehow you're going to call functions or classes, passing in something, you get a result, and then you just assert equal. So you say, hey, is the result I'm getting from my script the expected result? And that's all you have to do. So just be wary of this self.assert equal statement. Notice how it's casting self so that it's actually calling it from that test case inheritance. All right, that's it for talking about unit tests. It's actually quite straightforward, hopefully. If you have any questions, feel free to post the Q&A forums, but definitely take a look at the documentation for unit test. There's a lot more that it can do, but a lot of times, especially as you're just starting out, all you really need to do is create these simple assert equal statements in your class. Thanks, and we'll see you at the next lecture. Welcome back, everyone, to your second milestone project. So we've now learned enough about Python with object-oriented programming, errors and exception handling, as well as functions, enough to actually start a larger set project. And in this case, it's going to be our second milestone project, where we're going to be creating a blackjack game with Python. Now you can approach this project one of a few different ways. First off, if you're still feeling a little bit fuzzy on object-oriented programming, or you need more of a helping hand as you go along for your first large project, what you can do is just code along this project with the solutions lecture. A lot of students really like that approach, especially if they still feel a little bit too new to object-oriented programming. They'll jump straight to the solutions video and then code along with that actual video, and it's a nice way for someone to help guide you on creating a larger project. The second approach is almost the complete opposite, which is just to attempt the project on your own. So we actually suggest that students who feel very confident in object-oriented programming or who just like that extra challenge to, after viewing this lecture, just jump straight to a blank notebook or a blank script and get started. Debug, test things out, and play around with Python to see if you can build the game completely on your own. Then we kind of have an in-between, which is the workbook. So just like the first milestone project, we actually have a full workbook which breaks down the entire project into smaller, more handleable sub-problems for you to basically help guide you along as you attempt this project. And then there's a solutions lecture that goes through that workbook as well. So again, feel free to take the approach that is best suited for you, depending on how you felt with the material that we just covered. So as I mentioned, for this project, you're going to be using object-oriented programming to create a blackjack game with Python. So I want to quickly go over the main idea of the game, discuss how object-oriented programming should be used for this project, and then give you a brief overview of the workbook notebook for this project. So for our version of the game, it's going to be a simplified version of blackjack, where we're only going to have a computer dealer and a human player. And we're going to start with a normal deck of cards, and you're going to create a representation of that deck with Python using object-oriented programming. So let's quickly just go over what our actual game will look like. This is for people who are unfamiliar with blackjack, or if you are familiar with blackjack, we're going to discuss things that we don't need to consider or we'll just ignore for our version of the game. So the very basic concept of the game we're going to implement with Python is that we have the computer dealer and then the human player at the keyboard and a deck of 52 cards. Then what happens is the human player, they have a bankroll, so you can hopefully already start thinking that they're going to have an attribute for their bankroll, just like we discussed when we talked about creating a bank account for our previous object-oriented programming challenge. And from that bankroll, the human player is going to place a bet, indicating whether or not they think they're going to win this set of hands. Then what happens is the player starts with 2 cards face up, and the dealer starts with 1 card face up and 1 card face down. The player goes first in the gameplay, and the player goal is to get closer to a total value of 21 than the dealer does. And the total value is just the sum of the current face-up cards that the human player has. And there's 2 possible actions that a human player can take. They can either hit, which is to receive another card from the deck, or they can stay to stop receiving cards. We're going to ignore actions like insurance, splits, or double downs, which happen in a real casino playing blackjack, but we want a simplified version of this game. So all the player has to be able to do is hit, which is to grab a card from the deck and put it in their hand, and then take a new sum there, or stay, which means stop receiving cards. So for example, they could hit, get a new card, and then they check what their sum is. And remember, they're trying to get closer to the value of 21 than the dealer will. So once the player has gone, their turn has ended, and then it's the computer's turn. If the player is still under 21, then the dealer hits until they either beat the player or the dealer busts. So by bust, we mean that you go over 21. So let's see possible ways that the game can end. First off, if the player keeps hitting before the computer even goes and they go over 21, then they bust and they lost their bet. The game is then over and the dealer collects the money. So that's one way that the game can end, which is the player busting. And this is before the computer dealer even has to go. The second way the game can end is if the computer beats the dealer. So what happens is the human player goes, they start collecting cards, and then they decide to eventually stay. So for example, their current sum is 19. Then the computer dealer goes and they start hitting cards, so they collect cards from the deck. And if they have a sum that's higher than the human players and is still under 21, then the computer has beat the dealer. And then finally, the third possible option that the way the game could end is that the player actually wins after the computer has its turn. So in our simplified version of the game, what's going to happen is the computer dealer keeps hitting until they either beat the human player or until they bust. So eventually what may happen is they keep hitting and then they bust, meaning they go have a sum over 21. And if that's the case, the human player wins and they actually then double their bet money and that goes to their bankroll. And we have a happy human player. So let's talk about a few special rules that you're going to have to implement. One is that face cards, such as the Jack, Queen, and King, are going to count as a value of 10. So we're going to be walking you through how to actually create a representation of a deck of cards, and those face cards are going to have a sum value of 10. And then here's the tricky one, is that aces can count as either a 1 or 11, whichever value is preferable to the player. So if you have an ace in your hand, you can either treat it as a 1 or an 11. You can check out the resource links for more explanations of blackjack and more information on that, but what we're going to do now is explore the project itself and the workbook. Let's get started by jumping over to that repository. Okay, so here we are at the repository. If you go to Complete Python 3 Bootcamp, you should see a folder that has the milestone project. Keep in mind that the numbering might be a little different if we add folders in the future or rearrange things, but the name should be the same, Milestone Project 2. And what we see here are a few notebooks. We have the assignment notebook, and if you click on the assignment notebook, it basically just describes what the blackjack game is going to look like. We create a simple text-based blackjack game, players stand, hit, keep track of players' money. This is basically what I just described in those slides. And then the next couple notebooks is a walkthrough steps workbook. If we check that out, here we see walkthrough steps workbook. It's basically a kind of setup guide to how you should try to approach this project. And these are the basic steps you should follow when creating the game of blackjack. And then if you keep scrolling down, we have cells with some essentially skeleton code here for you to fill in. So you can see we've created a class card for you. We have an empty init method, an empty string method for you to fill out. And then we have step 3, create a class deck, step 4. So this is to help guide you. And it's kind of an in-between between trying to do it all on your own at first or from trying to just jump straight and treat it as a code along project. Although that's totally fine. Either of those approaches is okay too. We try to give you as many options as possible for different learning styles. So this is a workbook just like you had for the first milestone project where we slowly guide you through the various steps of creating this game. And at the very end, you're going to have what is essentially just a while loop here that goes through all the steps of the game. Then after that, the other two notebooks, one is the solution notebook that we're going to be going over in the next lecture. And then we also have a solution code notebook, and that's basically all the code that is in this workbook for the solutions in one cell. So in case you prefer using Sublime Text Editor or PyCharm or something that uses a .py script, you can use that solution code. That way you don't need to copy and paste from all the various cells in the workbook. Okay, so that's basically it. Again, you kind of have three approaches here. Treat it as a code along lecture by just jumping straight to the solutions. And I would recommend doing that if you feel a little uneasy still with some of the object-oriented programming topics. This is pretty much the largest piece of code you're going to be writing so far. So a lot of students tend to prefer that code along project. The other way you can do it is by going through the workbook itself, the one we just described here, seeing how far you can get, referencing the solutions when you need to. And then the third way for more experienced programmers, maybe people coming in from another language, or people who just want that extra challenge, open up a fresh notebook and just get started and see how far you can go. Again, we're always here to help out in the Q&A forums. If you have any questions, you can feel free to ask there. We'll see you at the next lecture where we begin going over the solutions. Welcome back, everyone. In this lecture, we're going to start going through the Walkthrough Steps Workbook solution. I want you to keep in mind this is just an example solution. There's basically an unlimited number of ways you could have gone through this project, but in this case, we're going to go through the steps in the workbook. Let's get started. Okay, so here we are at the workbook. Lots of different things to get started with on the gameplay aspect. What we're going to do in this lecture is just go through these various steps and then fill out all the cells and see if we can create some logic at the end to actually get the game running. So here we see the game, and we want to set some imports and global variables. So global variables, those are variables we're going to be able to reference in other functions and objects. So we first wanted to import the random module. That was actually already done for us, and that's going to allow us to shuffle the deck prior to dealing. And you can check out the useful operators lecture if you want to review about how to shuffle from the random library. But what we want to do now is declare a couple of variables to store the card suits, the ranks, and the values. And you can develop your own system, but we actually have a lot of the code here for you. Where suits, we're going to set it as a tuple. So I'm going to copy and paste this here. And then the ranks, we have 2, 3, 4, 5, 6, all the way through Jack, Queen, King, Ace. So we can set that up as well. Again, you didn't have to do it this way. This is just so to follow our system along with the workbook. And then probably the most important part was this values. And this values is a nice dictionary where you can pass in the rank of a card and then get out its actual numerical value. This is really useful to us because when we're dealing with cards like Jack, Queen, King, we're not going to be able to directly read off the number itself, such as 2, 3, 4. So what we can do is just use this dictionary as a lookup so we can enter Jack into the values dictionary and get back 10. We'll set Ace right now to 11, but later on we'll deal with that special factor where it can be either a 1 or 11. So we're going to copy this and also paste this here. And then finally, we're going to declare a Boolean value to be used for controlling the while loop. Just like we did in that tic-tac-toe project, it might be nice to have a while loop that's dependent on some variable, such as game on, and in this case, we'll set it as playing is equal to true. So later on at the end, we can set playing equal to false if the game is over. I'm going to run that cell and move on to the class definitions. So what we wanted to do now was create a card class. And the card object actually really only needs two attributes the way we're going to set it up here. It just needs a suit and a rank. And then we want to have a string method on it so that when we actually print a single card, we get back something in the form of 2 of hearts or 3 of clubs. So let's set this up. Here we can see the init method, and we're going to add in two attributes, suit and rank. And then we'll assign those. Self.suit is equal to suit, self.rank is equal to rank. And then for the string representation, again, you have a lot of flexibility here, but we're just going to return something like self.rank concatenated with of, notice my spacing there, concatenated with self.suit. So we run that, and now we have a basic card class. And I want to note that it's okay if you either have open close parentheses here or no open close parentheses. It's only when you're using inheritance that you really need them. I usually prefer having the parentheses there. The notebook itself doesn't have them. It's really up to you which styling you prefer. And now we move on to step 3. So for step 3, this is where we wanted to actually store the 52 card objects into some sort of list that we could later shuffle around. And there's already a lot of code that's built out for you here. So we can see what the code is doing. We set self.deck as an empty list. And what's important here to note is even though this deck object has this attribute, self.deck, you can call it really whatever you want, it's not taking it in as a parameter when you actually first initialize an instance of the deck. And that's because when you initialize the deck of cards, you want it to be the same every time. You don't want the user to be able to input a parameter that would make something different with the deck. Instead, a deck should just be a standardized thing. So what we do here is we say, set the deck as an empty list, and then for every suit in suits, remember suits, if we come back up here, that's our global variable, so we're going to be able to access it. For every suit in suits, and then for every rank in ranks, what we're going to do is, like the instructions say here, is actually append these using the card class. We'll say self.deck. So remember, that's an empty list. And then I'm going to append using the card class that we defined above. Remember, the card class just takes in a suit and a rank. We're going to pass those in as well, suit and rank. And now, after I initialize this, I should have a list of a bunch of card classes. Now for the actual string representation of this, it's really up to you how you want to represent your deck. In our case, we decided to do something like this. And remember, this function only really gets called if you actually print out your deck. So we'll start off the deck composition as an empty string. And we'll say for every card in self.deck, we're going to say that the deck composition, we're going to concatenate a new line. Let's make sure we have our quotes there. Plus the string representation of the card. So remember, card here has its own string representation, and we can call that using the following method. We can say deck composition, new line, plus card, and then string, and to actually execute it, we have open close parentheses here, which basically just calls print out the actual string representation of each individual card. So now we have this giant string with new lines, and at the end, we can just return back a string that says the deck has, and we can add in this deck composition. Then we can shuffle the deck. We actually showed it already here for you, but using that random library that we imported earlier, we just call shuffle on a list, and it will shuffle that list. Notice here, I'm not saying return. This actually happens in place. So this goes back to our discussion of object-oriented programming, where not every single method actually returns something. In this case, we're just shuffling that list in place. Finally, I want to have a deal method, which is a way to actually grab a card from my self.deck attribute, that list of card objects. So we'll say a single card is just equal to self.deck.pop. And this sort of syntax can be confusing for beginners, so I want to take a closer look at it. All we're saying here is basically two things. Grab the deck attribute of this deck class, and then pop off a card item from that list, and then set that to single card. What's confusing sometimes for beginners is that they see these two dots in a row, which is a little weird if you haven't seen it before. But in this case, it is just doing one single method off a list object, just like we did up here, where we said append off this self.deck list attribute, which is this. Once we pop off that single card, we can just return it. And technically, you didn't have to do this in 2 lines. You could have just said return self.deck.pop, but hopefully this commentary helps you understand what's actually happening here. So now we have our deck object ready to go. So let's do a little bit of testing. We should be able to create a test deck and then print out the test deck. We should then print out the deck has and this deck composition that we defined up here. So let's run this. And as you see, deck has 2 of hearts, 3 of hearts, 4 of hearts, 5 of hearts. So notice here, everything is in order. So let's do a little bit of testing by actually shuffling. So we'll say after creating the test deck, grab that test deck and shuffle it. And then instead of printing everything out in order, we should see something printed out shuffled. We run that and we see some diamonds, hearts, clubs, etc. And we can see that it's all been shuffled. So it looks like our deck class is working. All right, let's have a quick review before moving on to the next lecture of what we've done so far. At the very beginning, what we did was we set up some global variables. We also imported the random library. The global variables are a tuple to represent the suits, some ranks, which is another tuple to represent the ranks, as well as values. And this is a really important variable because it's a dictionary lookup where you just pass in the rank and you get back its numerical value so that you can easily take sums of someone's hand. Then we created a class for the card itself. So this represents just a single card, and it has 2 attributes, a suit and a rank, and you can print out a card and it will report back rank of a suit. Then for the deck class, we wanted to leverage that card class in order to quickly create 52 of every single card. To do that, we just have a nested for loop where we say for suit and suits, for rank and ranks, and by creating a empty list for this first attribute, we went ahead and took that list and appended a bunch of cards to it. Remember that card is an actual card object where we said for every suit in that global variable suits, so that's the one up here, and then for every rank in that global variable ranks, that's the one up there. We went ahead, created a card class, so now we have a card object and we appended it to that list. So self.deck is a list of these card objects. Then we wanted to be able to print out the actual deck, so if you said print deck, you'd get something. And in that case, all we do is we say, okay, start off with an empty string, and then for every card in this list of card objects, go ahead and concatenate a new line, and then the string representation of that card. And then we can print out the deck has, and it's just one giant string with a bunch of new line calls. So then when you actually print it out, you get back a list of all the cards. Then we can shuffle the deck, which is basically just calling that random.shuffle method on that self.deck list. And then we have deal, where we pop off a card object and we grab it by returning back that single card. Okay, and then we tested it out by creating a deck, shuffling it, and printing out the test deck. Coming up next, what we're going to work on is creating a hand class and then creating a chips class. We'll see you at the next lecture. Welcome back, everyone. To continue where we left off last time, we're going to create a hand class and a chips class. I want to quickly review what we did last time because we're going to be using it to actually create our hand class. Let's come back up to the very top very quickly. Remember that we have these suits, ranks, and values. These are global variables that we can easily use. And most importantly, we have this values dictionary. That means I can pass in a rank, such as 2 or 3 or 4, and immediately get back its actual value for the sum. We're going to be using that in the hand when we want to calculate the value of a hand. What we'll be able to do is pass in the actual rank of the card and then get back the value itself. After that, we actually created instances of card classes. So what that means is we basically have this card object where the card object has a suit and has a rank. That means we should, when passing in a card, grab the rank attribute and pass that into the values dictionary in order to get back an actual numerical value. Then moving on to the deck class, this was just a way to quickly create 52 unique card objects to represent each card in the actual deck. So we can see here that we used a nested for loop. So for suit and suits, for rank and ranks, we went ahead and appended these card objects where we passed in the suit and ranks. We also created a way to print them out, shuffle the deck, and then deal from the deck. Now it's time, if we scroll down here, to actually create a hand class. The hand class is basically going to represent what cards are currently in someone's hand. So the hand class, when you start off, it's going to start with an empty list, and then we're going to add cards from the deck. So we'll be, if you come up here, calling deal from the deck, and then grabbing that single card, and then adding it to someone's hand, which is what we're going to use when we call this add card method. So remember, that's going to be an actual card object. Then we have a value attribute to the hand, which is just the current sum of the value for that hand. And then we also want to keep track of aces in the hand because recall that aces have that special rule where they can either be a 1 or an 11. So let's start with this method for adding a card. What we're going to do here is say self.cards, and then we're going to append the card that's added. So here I have an empty list, and I will say self.cards of that empty list, append the card object. So don't get confused here, the fact this is a lowercase c. Keep in mind that the card passed in is actually going to be from this deck right here, meaning we're going to call deal off of this deck in order to actually grab a single card from it. So that's what this card represents. Later on, when we're saying add card, this is going to be from the deck, and it's going to be deal. Because remember, deck.deal, that's just a single card object. And the card object itself has a suit and rank to it. So I'm going to say self.cards, append that card, and since we know that this card object has a rank to it, we're going to be able to use that rank to get the value. So how do we do this? Well, we grab that card rank. Remember, that's going to be 2, 3, king, ace. And then we pass that in to the values dictionary as a key. And that's going to return back some number representing the value for that particular card's rank. And we'll take that value and add it to our current value. So we'll say self.value plus equals values card.rank. So a lot of stuff is happening in just 2 lines of code here. We're taking in a card object that we'll eventually call from deck.deal. We're appending it to this hand's current list of cards, and then we're adjusting our value to the card that was just added to this list. We're going to take that card's rank, look it up in the values dictionary that we did at the very beginning, and then we'll add that to our self.value, which is just some number of what the current value of the hand is. And we know when self.value is greater than 21, then whoever has this hand has lost. Okay, so let's do a little bit of testing before we tackle this issue of adjusting for an ace. So I'm going to do Alt-Enter here to create a new cell below. So Alt-Enter a couple times can create a couple of cells for us. Let's say that our test deck is equal to an instance of deck. Then I'm going to shuffle the deck. So we'll say test deck, call shuffle on it. And now we're going to create a test player. So this is the human player, and we'll be using a very similar thing for the computer, where we say the test player is now represented by this hand. And the test player starts off with no cards, no values, and no aces. Then we'll say test player, and let's add a card to their hand. So to add a card to their hand, we need to grab one from this deck. So I can say that I pulled a card from the deck. So pooled card is equal to deck, whoops, it's actually equal to test deck. And then notice I can say deal. So let's break this down. We define the player, going to deal one card from the deck. Remember, that is a card object. So it's actually a card that has a suit and a rank to it. Let's go ahead and then print out that pooled card. And then once we've printed out that pooled card, I'm going to add that card to the test player's hand. So we'll say add in the pooled card there. And then let's say, what is the test player's current value? We'll say test player value. Just call that attribute. Let's run this. All right, so what happened was we created a deck, we shuffled that deck, we created a test player represented as a hand object. So that test player's hand, we got test deck, we dealed something out, meaning we just got one single card, printed that card, so it reports back two of spades. Remember, each card has a string representation. And then we added that pooled card to the test player, and then we printed out the test player's value. Now we can actually do this in much fewer lines. What we can do is with that same test player right now, I'm not going to rerun this cell. I will say add a card, and inside of this, remember the pooled card was just test deck.deal, so I can copy that and paste it in here. And that's going to be adding another card to the test player's hand. So I run that, and now let's check our test player's current value. And now it has a 12. And now we can do this over and over again to keep adding cards to this test player's hand. However, what we still need to do is adjust for the ace. Okay, now it's time to actually tackle that issue with the aces. First off, let's take a look at our attribute self.aces. Self.aces, remember, allows us to actually keep track of the number of aces we have. So it might be a good idea that inside of this card method, what we can do is track our aces. What I will say is if the rank of that card is equal to ace, then I will say self.aces and add 1 to the count. So that means now aces is going to be 0 or some other number as I track the actual aces here. So if card is equal to ace, then self.aces plus 1. Then we need to adjust for ace. So there's two things that are going to have to happen here. We need to say while self.value is greater than 21 and self.aces, take our current value, subtract 10 from it, and then take our current number of aces and subtract an ace from it. Okay, so this is some really clever code here, which is why it's a little bit hard to read. So I want to break down what's actually happening here. We first have the check of self.value greater than 21. That makes sense because we're not going to adjust an ace to be equal to 1 unless the value is over 21. Because if we take a look at our initial values dictionary, when you first get an ace, you're going to consider it to be 11. So keep that in mind. What's going to happen is, let's come back up here. When we first get that ace, we're going to consider it to be an 11. Then, if we have that ace, we want to adjust for it. So I'll say if total value greater than 21, and I still have an ace, then change my ace to be a 1 instead of an 11. So that's the logic that we're trying to explain here. And that's what these 3 lines of code are doing. They're checking, hey, is my current value greater than 21? And self.aces. This one of and self.aces is a little bit tricky because you're using an integer as what's known as truthiness. So this means that we're actually treating this .aces integer as a Boolean value. And I want to show you what that looks like. Let's imagine that you have some number equal to 0, and then let's actually just call it 0, and then say 1 is 1, 2 is 2. If we check if these things are true or not, so if 0 print true, notice what happens. We don't get anything printed out. So that means if 0, the actual integer, it's treated as false. So 0 has a truthiness to it, where it actually is being treated as false. And other numbers that are not 0 are treated as true. So you can think of zeros, or any number besides 0, is going to be printed as true. So this says if 1, print true. So it's treating the integer 1 as true. And it's going to continue for integers that are not 0. So we're able to take advantage of that in our call right here by saying and self.aces. The other way you could do this is say and self.aces greater than 0, and that's pretty much the exact same thing. The code in the notebook just says self.aces because it's a kind of clever use case, but it's the same thing to say and self.aces is greater than 0. So you can keep either version here, but all it's saying is while my value is greater than 21 and I still have aces, then take my value, subtract 10 from it, and then take my aces and subtract 1 from them. Because now I've officially switched that ace, that instead of it's an 11, it's now going to be a 1. Okay, let's rerun that and then move along to creating our chips class. Our chip class is actually going to be super simple. Basically what we do is we just have sum total of chips. And if you want, what you could do is instead of just setting the total by default to be 100, you could say self total equal to 100. It's really up to you if you want it to be supplied by a user input, so they can say I start with 1,000 chips or 5,000 chips and then set total here, or the way the notebook shows is just automatically set it equal to 100. Don't allow for people to kind of make up money for themselves. Then for the win bet, we'll imagine that if they won a bet, we will say self.total plus equal to whatever their bet was. And if they lose bet, it's the reverse. We'll say self.total minus self.bet. And that's chips, that's all it is. We just keep track of some total and the current bet that they've placed, and then we either subtract that bet if they lose it, or add that bet if they win it. Okay, so that's it for this lecture. Coming up next, we're going to define some functions that will actually help us play the game. Let's quickly review what we created so far with our hand class and our chips class. Our hand class is basically a representation of the player, either the computer dealer or the human player. They start off with cards, they have some value associated with their current hand, and then they have some count on aces. To add cards, they just pick a card from the deck, append it to their current list of cards, and then they adjust their value accordingly by looking up that card rank in the values dictionary. Then they also keep track of aces, so they do an additional check. If that card rank is equal to ace, they add an ace number to it, just count 1. Then we can adjust for ace, which means if the self.value of my hand is currently greater than 21, and I still have aces, I'm going to adjust the ace to reduce the value to be a 1, so go from 11 to 1, we subtract 10, and then subtract 1 from my ace count. And then I've done the adjustment. All right, coming up next, we're going to go along with step 6, where we write functions for actually playing the game. The chips class itself was just adding and subtracting some bet from the total. We'll see you at the next lecture. Welcome back. Now it's time to actually create the functions that we'll be using when we run the larger piece of code at the end that actually plays the game. And there's a lot of flexibility having these functions, so don't take the instructions here as the only correct way to do this. We're going to start off by creating a function called takeBet that is going to ask the user for a bet and then set that as the actual bet. So let's do the following here. We'll say takeBet and we'll pass in some chips, and then we will say while true, we're going to try the following. We'll say chips.bet is equal to the integer of the input. How many chips would you like to bet? Question mark, space. And then we'll say except, so if they didn't actually input an integer, maybe they put in a letter, we'll say print, sorry, please provide an integer. Then we can say else if chips.bet is greater than the total number of chips available in this object. You'll say print, sorry, you do not have enough chips. You have, and then we can insert how much they have. So we'll say dot format chips, total number of chips there. Else, we're going to break out of this while loop. So this is just one way we could have done this. You didn't actually have to pass in the chips here. There's an example in the notebook, which I'm going to drag over real quick, just so we can see it. Here we can see that there's another method you could have done this that would not have taken in a chips object. Instead, if you knew in advance that you were going to call a particular player's chips object, you could have just called player chips here .bet. So it's really up to you, depending on how you can call this function, whether you want to pass in any arguments or not. Usually, when you're calling a function, you're going to want to pass in arguments. That way, you can have control of the global variables without needing to call that global keyword. Again, it's really up to you, whichever version you prefer. So we'll go with the version that we have where we're actually asking for the chips. So let's break this down what we just did. We take in some chips. Remember, that's the class we just said here, and it has a total and a bet attribute. We set the bet equal to whatever the player wants to bet. We say except if they're not providing an integer, and then we do a quick little check that even if they did provide an integer, we want to make sure that the bet is not greater than the chips total. And if that's the case, we'll print out a little message telling them how much they have left. Else, if that's okay and there's an integer there, we'll just break out of this while true loop, and we've set chips.bet successfully. So let's run this and now move on to step 7, which is to write a function for taking hits. This one's actually pretty straightforward. All we need to do here is say hand, and we're going to add a card to the hand from the actual deck. You could do this all in one line, or you could separate it out into 2 lines, saying something like single card is equal to deck deal, and then add in to that hand the single card you just defined, and we want to make sure that we adjust for the ace afterward. So we can say hand adjust for ace, and we'll call that method as well. All right, so now we have hit. It takes the deck and someone's hand, grabs a single card from the deck, adds it to the hand, and then checks for an ace adjustment. Step 8 is to write a function prompting the player to hit or stand. So this function, what it's going to do is going to accept the deck and the player's hand as arguments and assign playing as a global variable. And this is actually to control an upcoming while loop. You could just provide playing here in the function as well and then return it back. It's kind of up to you how you want to deal with it. But this is just going to be another while true loop, very similar to before. We will say x is equal to input, asking hit or stand, enter h or s. And then we'll say if x lowercase is equal to h. So why am I doing this? Well, maybe someone is going to misunderstand this line and then type out something like hit or something like hh. Maybe they do lowercase stand. In that case, what I'm going to do is be able to grab the string, grab the first letter of it, lowercase, and say if it equals h, they probably meant to hit. So I'm going to say hit from the deck on their hand, else if x0 dot lowercase is equal to s. I'm going to assume they want it to stand. And I'm going to say print player stands, dealer's turn. And I'll set playing equal to false. And this is because I'm going to use this in a while loop later on. You didn't have to do it this way. Again, there's many different ways you can control the while loop later on. This is just the way we're going to do it so that we can kind of clearly see it in the while loop later on. Finally, we'll have an else statement that says print, sorry, I did not understand that. Please enter H or S only. Because that basically means they didn't enter something that starts with an H or an S. Then I'm going to continue. And if none of those gets triggered, then what happens is we just go ahead and break. Okay, the next thing we want to do is write functions to handle each of the game situations where it's going to end. And remember to pass in the player's hand, the dealer's hand, and the chips as needed. So let's go ahead and pass those in. We'll say pass in the player, who's represented by a hand. Let's make sure we spell that right. Pass in the dealer, who's represented by a hand object, and then pass in the chips themselves. We'll grab these and pass them into all of them, except for push, because if there's a push, that means both player and dealer got 21, so we won't actually do anything with the chips. So here on push, that's the easiest one. We don't really do anything. We just say dealer and player tie, push. For the other ones, we're basically going to print a message out and then adjust the chips themselves. So if the player bus, we'll print out bust player. We'll take those chips and then we'll call the lose bet method off of them. Player wins, very similar thing. We print out player wins. We take those chips and then we say win bet. If the dealer bus, it's going to be the same thing up here. The player will win the dealer bus, except we'll add another message here. Player wins, dealer busted. If the dealer wins, it's going to be a similar thing to the player busting, except the message will be different. They'll still lose their bet, except we'll say dealer wins. Okay, run that cell. And now, the last thing we need to do is actually run the logic of the game. We'll be doing that in the next lecture, but let's quickly review what we did in this lecture. So we started off by creating the actual functions that we're going to be calling in the next lecture. We first started off with take bet, which is just in some form or manner getting an input from the user and then setting it to the current bet. Lots of different ways you could do this. Then we wanted to write a function for taking hits, so we take in the deck, we take in a hand, we take in a single card from the deck, add it to the hand, and then adjust the hand for an ace. Then we wanted to write a function prompting the player to hit or stand. Basically, we just wanted to figure out, hey, am I going to call hit, or am I going to just stand and say that this current player is no longer playing, or I can just continue if they didn't provide an H or an S. Then I wanted to write functions to display the cards. Lots of different ways you can do this. You can check out the notebook for some more advanced one-liner ways of displaying all of this information. And then we wanted to write functions to handle each of the game situations where we basically either call lose bet or win bet and print out a message. Coming up next, we're going to code out the logic for the entire game. All right, let's get started with actually programming out the game. We're going to print some opening statement. In this case, we'll just do something simple like welcome to blackjack. And then we want to create and shuffle the deck. So we'll say deck is equal to an instance of a deck object. And then we'll grab that deck and we will shuffle it. After that, we want to set up the players themselves. So set up 2 hands for each player. Or I should say a hand per player, hand per dealer. So player hand is equal to an instance of the hand. And we're going to grab that player hand and then add a card to it. And the card itself is going to be just dealing from that deck. So we'll say deck.deal. And we're going to do this twice. And we'll actually do a very similar thing for the dealer. So we're going to copy and paste this code, except instead of the player hand, it will be the dealer hand. So we'll say dealer, create a hand, add a card to this twice. So we created a deck, and now we have a player hand and a dealer hand. Up next is to set up the player's trips. So for this, we'll say player chips is equal to a chips object. Remember, the default value is 100, but you could adjust this depending on how you define the actual chips object above. Then up next, we want to prompt the player for their bet. So we already have the take bet function that does this for us. We say take bet, and we're going to pass in the player's chips. And then we want to show cards. So in this case, this is still the beginning of the game, so we'll only call the show sum function. We'll say show sum, and then we'll pass in the player hand, the dealer hand, and then we'll also pass in, actually that's all we need to pass in for show sum. And then while playing, recall this variable from our hit or stand functions. This is a global variable here. So while we're playing, we're going to ask the player, do they want to hit or stand? So we actually have this hit or stand that takes in the deck we created, as well as the player hand. Then we want to show the cards. Since the player is still playing, we're going to say show sum again. And it's actually the same here as above, show the player hand and the dealer hand. So we'll copy this and paste it in. Then if the player's hand exceeds 21, we're going to check or run player bus. So we'll say if the player hand, I should say the value of the player hand, remember that's an attribute. If it's greater than 21, then this player has busted and they've lost. So we will call player bus and then pass in the needed information, including the player hand, the dealer hand, and then the player chips. After that, we can just break. So let's go over what we've done so far. We've set up the deck, we set up the player's hand, and we set up the dealer's hand. We set up the player's chips, we've taken a bet from the player, and then we show some of the cards. Basically, show some means still show that dealer's hand as one of the cards face down. Then while playing, we will say hit or stand for that player. We'll show some of the cards. Let's make sure that lines up there. And then if that player's hand value is greater than 21, we're going to bust out of that. Now for the next step, we want to check if the player hasn't busted. We're going to play the dealer's hand until the dealer reaches 17. And I'm going to explain that in just a second, but let's write out the code for it. We'll say if the player hand value is less than or equal to 21, that means the player hasn't busted. And we're going to say while the dealer hand value is less than 17, go ahead and hit using the deck and the dealer hand. Something I want to note is it depends on how you want to set up your game, whether or not you want to use the value of 17 here. If you're familiar with the game of blackjack, in a casino they have this rule called soft 17, that the dealer only hits until they reach 17. Now, the way you could have also structured it is say, while dealer hand value is less than the player hand value to keep on hitting. It's up to you whether you want to do this soft 17 rule, or if you want to just keep going until you either beat the player or bust. So either one of those methods is okay. Again, it really depends on how much into detail of the game of blackjack you want to go into. Right now, we're really just focused on coding, so either one of the options is fine. So since the dealer is now playing, we need to show all the dealer cards. We will say show all, and we'll say player hand and the dealer hand. And I'm just using tab to autocomplete there. Then we run the different situations where someone may win or lose. So if the dealer's hand value is greater than 21, then the dealer has busted. So we say dealer bus, and we pass in the player hand, the dealer hand, and the player's chips. If the dealer hand value is greater than the player hand value, then the dealer has won. So we'll say dealer wins, and then we pass in the same three parameters as before. So let's copy that and paste them in. Else if we have another situation to check, so we'll say elif the dealer hand value is less than the player hand value. And this is more dependent on that soft 17 rule, because it kind of depends. If you initiated this as 17, then this situation may come up. If you just keep going until you bust, then this situation won't ever come up. But we'll still pass it in here, so we match up the notes. We'll say player wins if the dealer hand value is less than the player hand value. And again, we just pass in the player hand, the dealer hand, and the player chips. Else, and then finally we check the situation for a push where they both happen to get 21 and they tied up. We'll say push on the player hand and the dealer hand, which are the functions we defined before. Then we want to inform the player of their remaining chips, so we're going to say print. We'll say print a new line just so we get some space here. Players total chips are at, and we'll end the string there and format in player chips total attribute. And then finally we'll just have some little small loop here to ask them if they want to play again. So we'll say new game is equal to input. Would you like to play another hand? We'll say yes or no. And if the result of the new game, if that first letter, let's say if that first letter lowercase is equal to a Y, we'll set playing equal to true, and then it's the player's turn again, and we'll continue along. Else, what we're going to do is say print thank you for playing, and then we'll break out of that entire loop. Okay, so we just did a lot of code here, so let's zoom out and run through all the steps here, and then we'll debug just in case we have any typos. So, the game. We say while true, we print out welcome to blackjack. This is the pretty straightforward stuff. We create a deck, we shuffle it, then we create a hand object to represent the player, add 2 cards to that hand, then we create a hand object to represent the dealer's hand, add 2 cards to that dealer's hand. We set up the player's chips, then we take a bet from the player, and then we show some of the cards. So we say player hand and dealer hand, and show some means that the dealer's hand is still hidden. Then we have this global variable called playing. And while we're still playing, that is the human player still playing, we ask them if they want to hit or stand. Then we show some of the cards, so the dealer's card is still hidden. And then we check, did the player bust or not? If they busted, then we just break out of this. If the player hasn't busted, that means their value is still less than or equal to 21. We check while the dealer hand value, and you can say either less than the player hand value or less than 17, depending on how you actually want to implement that rule, you'll keep hitting. Then you're going to show all the cards, and then you'll check for the different situations. Either the dealer's busting, the dealer wins, the player wins, or it's a push. We inform the player what their total chips are, we ask them if they want to play again, and then we have this little loop that will either reset the playing to true or we'll break out of this while loop. Let's run this and see if we get any errors. Okay, how many chips would I like to bet? First off, let's bet way too many chips and see if we get that error. So it says, sorry, you don't have enough chips, you have 100. Okay, so far so good. Let's bet 50 chips. Dealer hand, we get 1 card hidden, and they have the 10 of hearts. I have the queen of hearts and the queen of spades. Remember, that total value is 20, because that's 10 plus 10, so I'm definitely going to stand. I'm going to enter S here. So I stood, and then I have dealer's hand, ace of hearts, 10 of hearts. So that's a straight 21. That's pretty freaking lucky. But looks like we lost even with a great hand of 20. So I have total chips are 50. Do I want to play another hand? Yeah, let's do it. Let's see how good our luck is. Welcome to blackjack. How many chips would you like to bet? Let's see if I bet 100 again, what happens? So notice if I bet 100, I actually don't get an error because it's being reset the way we designed it. So I'm going to scroll up real quick just to show you this. So each time you call chips here, it's being reset because of the way we define chips. All the way back up here, we said by default the total is equal to 100. What we could have done is kept going with some sort of recurring chips object and not have it reset 100. It's up to you how you want to think about this, but you could assign chips instead to maybe a player. So let's continue along. We basically reset our number of chips. We'll come back down here and let's check what we have. Player's hand is an 18. I'm going to stand again. That's a pretty good hand to stand on. And we have dealer's hand was a 2, 6 of clubs, and an ace of diamonds, so that's 19. Dealer wins again. Player chips total. Let's say, yes, I want to play again. And I'm going to just put in a bet here. 1 card hidden, 10 of diamonds. I have 5 of diamonds, queen of hearts. So I can tell this game is definitely favored towards the dealer. Let's hit just so we can practice hitting. And now I have 5, 10, and ace, so that's 16. That's pretty lucky. We'll stand there. And let's scroll all the way down. You'll notice in Jupyter Notebook if you have too much. So it looks like the dealer ended up busting, so we won. So the dealer hand was too much. It kept going, and now we are at 120. Would I like to play another hand? No, thank you. Say no, and now it's thank you for playing. Okay, that's it for the entire game. That's definitely a lot of code. And keep in mind, your solution could look way different than this. There's basically an infinite number of ways you could have programmed out this game. You could have made more classes, used more functions, assigned maybe a player class and a dealer class instead of just hands for them both. So it's really up to you, the flexibility here. If you have any questions, feel free to post the Q&A forums, but this basically concludes the second milestone project. We'll see you at the next lecture.